Imagine a tower so tall that it bypasses the clouds, airplanes, and even the space station. We are talking about a space elevator, an idea for a cable stretching over 36,000 kilometers, connecting the Earth's ground directly to space. It would be the largest structure ever made by humanity and would change everything about how we travel to the stars. But here is the confusing part. Why haven't we built it yet if the idea has existed for over 50 years? It turns out the biggest problem is something we use every day: gravity. The sheer weight of such a long cable would break it before it even reached the clouds, unless it was made of a magical material that doesn't exist yet. Are we close to creating this material? Prepare to fall asleep while listening to this video as we explore this incredible challenge. Subscribe to the channel, leave your like, and comment where in the world you are watching from. Get comfortable and relax. Let's begin. Imagine a cable so strong it could stretch from the Earth's surface all the way into space, acting as a backbone for an elevator to the stars. The single biggest hurdle to making this science fiction dream a reality isn't the money or the rockets. It's finding a material that can actually do the job without breaking. This quest for the ultimate material is what truly defines the challenge of building a space elevator. And it's a problem that has stumped scientists and engineers for decades. Think about it. You need something that is unbelievably strong yet incredibly light. A combination that nature rarely provides and that we have struggled to create. Common materials we use every day, like steel, are completely inadequate for this task. If you tried to build a space elevator cable out of steel, it would snap under its own weight long before it reached the required altitude of tens of thousands of kilometers. The force of gravity pulling down on the cable itself would exceed the material's tensile strength, causing a catastrophic failure. This is because every meter of cable has to support the weight of all the cable below it, and that accumulated weight becomes astronomical over such distances. So, the search is on for a material with a high enough specific strength, which is a measure of its strength compared to its density. This is where advanced materials like carbon nanotubes come into the picture. Carbon nanotubes are cylindrical molecules made of carbon atoms arranged in a hexagonal lattice, and they have been the great hope for this application. Their theoretical tensile strength is hundreds of times greater than that of high-strength steel, and they are also extremely lightweight, which makes them seem like the perfect candidate. However, there is a massive gap between theory and practice when it comes to carbon nanotubes. While we can produce them in laboratory settings, we are currently incapable of manufacturing them in the macroscopic lengths and with the purity required for a space elevator cable. Right now, the longest carbon nanotubes we can create are only on the scale of centimeters, but we need continuous strands that are thousands of kilometers long. Producing such lengths without any defects is an enormous engineering challenge that we haven't yet overcome. Even tiny, atomic-scale imperfections in the structure of a carbon nanotube can drastically reduce its overall strength. In a cable that is under immense tension, a single weak point could lead to a chain reaction that causes the entire structure to fail. This sensitivity to defects means that the material must be virtually perfect, which is something our current manufacturing processes cannot guarantee. The process of creating long, pure carbon nanotubes involves complex chemical vapor deposition methods, but scaling this up to industrial levels while maintaining quality is still a distant goal. Furthermore, handling and weaving these nanotubes into a usable cable format present additional hurdles. They need to be aligned perfectly to maximize strength, and any twisting or misalignment could introduce weaknesses. Beyond carbon nanotubes, other materials have been proposed, such as graphene or boron nitride nanotubes, but they face similar issues with production scalability and defect management. The quest for this magic material isn't just about improving existing technology. It represents a fundamental revolution in materials science. It requires discoveries and innovations that we are only beginning to explore. For instance, researchers are looking into self-healing materials or composite structures that could mitigate the impact of defects, but these are still in early stages of development. The economic and time investments needed to advance this field are substantial, and there is no guarantee of success in the near future. Moreover, testing such a material would be a challenge in itself. You can't just build a small-scale model. The properties needed only become apparent at the enormous scales required for the full elevator. This means that any candidate material would have to undergo extensive simulation and limited physical testing, which adds to the uncertainty. The environmental conditions the cable would face also complicate the material requirements. It would be exposed to extreme temperature variations, from the heat of the Earth's surface to the cold of space, which could cause expansion and contraction, leading to material fatigue over time. Radiation in space could also degrade the material, affecting its long-term durability. So, the material doesn't just need to be strong initially, it must remain strong for years, even decades, under constant stress and harsh conditions. This demands not only high tensile strength, but also excellent resistance to fatigue, creep, and environmental damage. The search is further complicated by the need for the material to be flexible enough to handle dynamic loads, such as oscillations caused by weather or the movement of climbers, without developing microfractures. In essence, we are looking for a material that defies current understanding, one that combines the best properties of known substances while overcoming their limitations. This is why the development of a space elevator is often seen as a milestone for human civilization. It hinges on a material breakthrough that would have ripple effects across many industries, from aerospace to construction. Until we find or create this definitive material, the space elevator will remain a fascinating concept, but one that is out of reach. The ongoing research in nanomaterials gives hope, but the path is long and fraught with scientific obstacles. It's a classic case of a technological dream waiting for a key invention, and that invention is a material so advanced it might as well be magic for now. The entire endeavour teaches us a lot about the limits of our current capabilities and pushes the boundaries of what we believe is possible. So, while the idea of a space elevator captures the imagination, the reality is that we are still searching for that one material that can turn science fiction into science fact. This search is active in labs around the world, with scientists experimenting with different carbon allotropes and other nanostructured materials. They are trying to understand how to control the growth of these structures at the atomic level to eliminate defects and how to assemble them into larger, coherent forms. It's a painstaking process that involves chemistry, physics, and engineering, working in tandem. The stakes are high because success could revolutionize access to space, making it cheaper and more routine. But failure means we have to look for alternative methods or accept that this particular vision might not be feasible. In the meantime, other approaches to space access, like reusable rockets, are advancing. But the space elevator concept remains the ultimate goal for its potential efficiency. The material challenge is, therefore, the cornerstone of the entire project, and without a solution, everything else is moot. This underscores the importance of basic research and innovation in materials science, as it often holds the key to unlocking future technologies. So, the next time you hear about a space elevator, remember that it all comes down to a simple yet profound question. What is it made of? And right now, we simply don't have a good answer. The journey to find that answer is as thrilling as the destination itself, driving human curiosity and ingenuity to new heights. We are essentially trying to create a material that behaves unlike anything we have ever seen, with properties tailored to an application that pushes the limits of physics. This involves not just making a strong material, but making it in a way that is economically viable and scalable. Current methods for producing carbon nanotubes are expensive and energy intensive, which is another barrier to their use in such a massive project. Even if we achieve the necessary material properties, we would then face the challenge of manufacturing the cable itself, which would be the largest single structure ever built by humans. The logistics of producing, transporting, and assembling such a cable are mind-boggling. It would require new forms of engineering and construction, possibly in orbit or using automated systems. All of this hinges on that initial material breakthrough. So, the search for the definitive material is more than just a technical hurdle. It is the defining challenge that will determine whether a space elevator can ever be built. Until then, we continue to explore, experiment, and dream, hoping that one day we will discover or create the magic crystal that makes it all possible. This pursuit is a testament to human ambition and our desire to reach beyond our planet, but it also keeps us grounded in the reality of our current technological limitations. The path forward is unclear, but the quest itself drives progress, and that is something worth pursuing. But even if we somehow discovered that magical material strong enough to hold its own weight, we would immediately run into the next colossal problem: the relentless and unforgiving force of gravity itself. Gravity is not this constant, uniform pull we experience on the ground. It's a variable force that changes dramatically over the vast distance a space elevator cable must span. And this variation creates a nightmare of engineering challenges. Think of gravity as a tyrant whose grip weakens the further you get from its throne. But it's a deceptive kind of weakness. At sea level, the gravitational pull is at its absolute strongest, which means the very bottom of the cable, the part anchored to Earth, has to bear the incredible weight of the entire system stretching upwards for tens of thousands of kilometers. It's like hanging a rope from a skyscraper, but if that rope was long enough to wrap around the planet, the top isn't holding the bottom is holding the weight of everything above it. This accumulating weight is the first part of the tyranny. Now, as the cable extends upwards, something counterintuitive happens. The force of gravity from Earth does indeed get weaker with altitude, but simultaneously, another force comes into play: centrifugal force. Because the Earth is rotating, any object attached to a cable extending from it is also being swung around like a ball on a string. This centrifugal force acts outward, away from the Earth's centre, and it gets stronger the further out you go. So, you have this incredible tug of war happening along the entire length of the cable. At the bottom, gravity is dominant, pulling down. At the very far end, way out in space, centrifugal force becomes dominant, pulling outward and effectively trying to fling the cable away. Somewhere in the middle, these two forces must balance each other out. This equilibrium point is precisely at geostationary orbit, about 36,000 kilometers above the Earth, where a satellite orbits at the same speed the Earth rotates, so it appears stationary in the sky. This is the natural anchor point for the entire system. But here's the critical catch. This balance point is not a place of rest for the cable. It's actually the point of maximum stress. Imagine pulling on both ends of a rope. The tension is highest in the middle. For the space elevator cable, the tension is most extreme at this geostationary altitude because it's where the pull from the planet below and the flinging force from the rotation above are both exerting their full influence, stretching the cable to its limit. Designing a cable that can withstand this insane variation in forces is a physics problem of monumental proportions. The cable isn't just experiencing one type of force, it's dealing with a gradient of forces, a smooth transition from crushing gravitational compression at the base to immense tensile stretching at the balance point and beyond. This means the cable's design can't be uniform. It might need to be thicker in some sections and thinner in others, or even be made of different materials along its length to optimally handle the changing stress profiles. However, adding material to strengthen one area adds more weight, which in turn increases the load on the sections below it, creating a vicious cycle. Engineers call this the taper ratio point, which is the factor by which the cable's cross-section must increase from the top down to the bottom to support its own weight under these forces. For any known material, even theoretical ones like carbon nanotubes, this taper ratio is astronomical. It could mean that the bottom of the cable would need to be impossibly thick compared to the top, making the entire structure impractical from a mass and construction standpoint. This gravitational gradient is why the material's strength requirement is so unforgiving. It's not just about being strong, but about being strong enough over a changing force field that wants to tear it apart in different ways at different heights. Furthermore, this isn't a static situation. The Earth's gravity field isn't perfectly uniform. It has slight variations due to mass concentrations like mountains and ocean trenches, which could impose additional fluctuating stresses on the cable. The Moon and the Sun also exert their own gravitational pulls, causing tides that would make the cable sway and oscillate, adding dynamic loads to the already immense static tension. Managing these oscillations is a whole other layer of complexity, but the fundamental tyranny lies in that static balance between gravity and rotation. If the cable's design fails to account for this gradient perfectly, the result wouldn't be a slow failure. It would be instantaneous and catastrophic. A break near the anchor point would cause the entire cable to unravel and wrap around the Earth, causing devastation on a continental scale. A break higher up could send the upper section flying into space while the lower part crashes down. This precise balance is so delicate that even a small miscalculation in the material properties or the force models could lead to disaster. The gravitational gradient also affects the climbers, the vehicles that would travel up and down the cable. As a climber ascends, it's moving through this changing gravity field. At the bottom, it feels the full weight of Earth's gravity, requiring more energy to climb. As it goes higher, gravity weakens, but the Coriolis effect from the Earth's rotation comes into play, pushing the climber sideways and adding lateral stresses to the cable. The climber's journey isn't a straight vertical line. The cable itself would curve due to these forces, and the climber would have to navigate this curve, all while the tension environment around it is shifting. This dynamic interaction between the moving climber and the flexible cable under variable gravity adds another dimension of engineering headache. Moreover, the location of the geostationary orbit dictates where the elevator must be anchored. On the equator, this limits possible base locations to often volatile tropical regions, exposing the base and the lower cable to severe weather storms and lightning, which are additional risks on top of the fundamental physics problem. The tyranny of gravity and its gradient is therefore a dual challenge. First, it defines the extreme mechanical environment that the cable must survive, setting the bar impossibly high for materials science. Second, it dictates the entire architecture and operation of the system, from the anchor point to the counterweight beyond geostationary orbit. Overcoming this isn't just about building something strong, it's about building something smart enough to handle a force that changes its nature over an unprecedented distance. This is why many scientists believe that even with a material breakthrough, the gravitational gradient problem might be the ultimate showstopper. It's a reminder that space access is hard, not just because of the rockets, but because of the fundamental physics of our planet. We are trying to build a structure that contradicts the natural order of gravity's dominion, creating a bridge where the very rules of force change from one end to the other. Every meter of the cable exists in a slightly different gravitational context, and designing for that continuity is perhaps the most profound engineering challenge humanity has ever contemplated. So, while the search for the material is crucial, Understanding and conquering the tyranny of gravity's gradient is what will ultimately determine if we can ever step into an elevator and press the button for space. The force that keeps our feet on the ground is the same force that we must meticulously outsmart across 100,000 half-miles of cable. And that requires a depth of understanding and a level of precision that we are still striving to achieve. This isn't just about strength. It's about harmony with forces that have shaped our world since its beginning. So, building on that idea of harmonizing with fundamental forces, we quickly realize that the cable's own weight isn't just a factor, it's the primary antagonist in this entire story. The sheer mass of the material needed to span such an incredible distance creates a self-defeating loop where the structure's greatest weakness is itself. Imagine trying to lift a chain. The longer the chain, the heavier it gets. And eventually, the links at the top are holding so much weight that they break. Now, scale that chain up to a cable stretching into space, and you begin to grasp the core issue. It's not the cargo capsules or the climbers that pose the biggest structural threat. It's the relentless, cumulative burden of the cable's own molecules. Every single metre of that cable has a weight, and each metre must support not only its own mass, but also the entire weight of all the cable hanging directly beneath it, all the way down to the Earth's surface. This means the section of cable at the very bottom, right at the anchor point, is under the most crushing load, bearing the accumulated weight of tens of thousands of kilometres of material above it. But the problem is even more twisted than that. Because of the centrifugal force pulling outward from the Earth's rotation, the sections of cable above the geostationary point are also under immense tension, effectively pulling upward. So any given segment of the cable is being squashed from above by the weight below and stretched from below by the tension above. This creates a nightmarish stress profile where the cable is in a constant state of competing forces, and the total tension builds up in a way that is almost unimaginable. This accumulated tension over such a vast distance creates a load that far exceeds the capability of any material we currently know or can manufacture. When engineers talk about a material being strong enough for a space elevator, they aren't just comparing it to steel or diamond. They are evaluating it against a fundamental physical property known as the characteristic length. This is a theoretical calculation that compares a material's tensile strength to its density, and it effectively tells you the maximum length a cable of that material can be before it breaks under its own weight. For a space elevator to be feasible, the material's characteristic length needs to be significantly longer than the elevator's required height, which is around 36,000 kilometers. The depressing reality is that even the most advanced materials we have today, like the best carbon nanotubes we can produce in labs, fall short of this requirement by a huge margin, often by an order of magnitude or more. This means that if we tried to build a cable with today's top-tier materials, it would snap long before it reached the necessary length, simply because its own weight would cause it to fail. The quest, therefore, becomes not just for a strong material, but for an incredibly light and strong material simultaneously. Strength alone is useless if the material is too dense, as its weight becomes its own undoing. This is why common materials like titanium, or even the strongest alloys, are completely out of the question. Their density is too high, so their characteristic length is far too short. The focus has shifted to nanomaterials precisely because they offer the promise of extraordinary specific strength, which is the ratio of strength to density. Think of it as a measure of efficiency. How much load can a material carry per unit of its own weight? For a space elevator, the specific strength needs to be astronomically high. This is why carbon nanotubes and graphene are so tantalizing. Their theoretical specific strength is hundreds of times greater than that of steel, but theory and practice are worlds apart. The nanotubes we can currently make are riddled with microscopic defects at the atomic level. A single misaligned carbon atom or a tiny impurity can create a weak spot that, under the immense tension of the space elevator cable, could initiate a catastrophic failure. The cable is only as strong as its weakest link, and when you're dealing with a structure that is thousands of kilometers long, the probability of a critical defect existing somewhere approaches certainty with our current manufacturing capabilities. Furthermore, producing these nanomaterials in the macroscopic lengths required is another monumental hurdle. We can make centimetre-long nanotubes in labs, but we need continuous, defect-free strands that are thousands of kilometres long. There is no machine or process that exists today that can spin a carbon nanotube fibre that long without introducing flaws. Even if we could, the process would be impossibly slow and expensive. The scale of production needed is beyond anything humanity has ever attempted in materials science. We are talking about manufacturing a single object with a mass of millions of kilograms, all composed of a perfect, nearly flawless nanomaterial. The energy and resource requirements for such an endeavour are staggering. Moreover, the cable wouldn't have a uniform thickness. To manage the varying stress along its length, engineers propose a tapered design, where the cable is thickest at the geostationary orbit level, where tension is highest, and thinner towards the ends. However, this taper ratio, the factor by which the cross-section changes, is brutally demanding for any material. For a material with a moderately high specific strength, the taper ratio might require the cable to be impossibly thick at the bottom, making the whole structure so massive that it becomes impractical. Only a material with an exceptionally high characteristic length allows for a manageable taper ratio, meaning the cable can be relatively thin and consistent throughout, which is crucial for keeping the total mass and cost within the realm of possibility. This self-weight problem also interacts dangerously with other issues. For instance, the oscillations and vibrations we discussed earlier would be exacerbated by the cable's own mass, creating dynamic loads that could amplify stress at certain points. A swaying cable has inertia, and the heavier it is, the more force is involved in those swings, increasing the risk of fatigue or snap. Additionally, the cable's weight affects the anchor station, which must be designed to handle not just the downward pull but also the shifting loads as the cable moves. The counterweight at the top also has to be massive enough to keep the cable taut against the pull of gravity on the lower sections, but that adds even more mass to the system, creating a feedback loop. All of this underscores that the challenge of self-weight is inextricably linked to every other aspect of the elevator's design. It's a foundational problem that doesn't have a simple workaround. We can't just add more material to make it stronger, because that adds more weight, which makes the problem worse. This is why the search for the perfect material is so desperate. Scientists are exploring not just pure carbon nanotubes, but composite materials that might blend nanotubes with other elements to improve toughness and reduce the likelihood of defect propagation. Other ideas include using boron nitride nanotubes or crystalline materials that might have better inherent properties, but these are even further from practical application. The research is also looking into self-healing materials that could automatically repair small cracks caused by micrometeorite impacts or fatigue, but that technology is in its infancy. The economic implications are also huge. Developing a material with the required characteristic length would require billions of dollars in research and development, and there's no guarantee of success. Private companies and governments are investing in nanomaterials for various reasons, but the specific goal of achieving space elevator grade strength is not a primary driver because the payoff is so distant and uncertain. In the meantime, alternative concepts like space fountains or launch loops are proposed, which might avoid the self-weight issue by using different principles, but they come with their own massive engineering challenges. The space elevator remains the holy grail because of its elegant simplicity in concept, but the implementation is a nightmare of physical constraints. The problem of self-weight and tensile strength is a stark reminder that sometimes the biggest obstacle to a grand vision is not the complexity of the systems we build, but the fundamental properties of the stuff we build them with. Until we can create a material that is almost ethereally light yet stronger than diamond on a macroscopic scale, the space elevator will remain a dream, a testament to an engineering problem where the enemy is not the load we carry, but the very backbone meant to carry it. This pursuit pushes the boundaries of chemistry, physics, and manufacturing, and while progress is being made in nanomaterials, the gap between what we have and what we need is still vast. It's a humbling challenge that shows how much we have yet to learn and invent before we can truly conquer the final frontier with something as straightforward as an elevator. Even if we somehow conquer the monumental challenges of material strength and the cable's own weight, a new and terrifying enemy emerges, one that is already silently menacing our current assets in space. The relentless and growing cloud of orbital debris. Picture this, a pristine, incredibly thin cable stretching upward from Earth, passing directly through a celestial junkyard filled with defunct satellites, discarded rocket bodies, and millions of tiny fragments, all travelling at velocities exceeding 28,000 kilometers per hour. This isn't some distant future problem. It's a present-day hazard that the International Space Station regularly dodges. But for a stationary structure like a space elevator, it becomes an unavoidable game of Russian roulette on a cosmic scale. The sheer volume of this junk is staggering. There are hundreds of thousands of tracked objects, and millions more too small to monitor reliably, ranging from entire dead satellites to tiny screws and flakes of paint. Each of these pieces, regardless of size, carries devastating kinetic energy because of its incredible speed. At those velocities, which are about 10 times faster than a bullet from a high-powered rifle, a paint chip can hit with the force of a falling anvil, and a metal bolt a few centimetres across could deliver an explosive punch comparable to a large grenade. Now, imagine a cable that might only be a few centimetres thick in its cross-section, stretched taut across tens of thousands of kilometres. It presents an enormous target profile that cannot move out of the way easily. The probability of impact over time approaches certainty. It's not a question of if it will be struck, but how frequently and by what size of debris. An impact from even a small particle could create a microscopic crack or crater on the cable's surface. In most structures, a tiny flaw might be tolerable, but in a cable under immense tensile stress, that small imperfection becomes a focal point for stress concentration. Under the constant pull of gravity and centrifugal force, that tiny crack could propagate, slowly growing with each vibration and load cycle until it leads to a catastrophic failure. A larger piece of debris, something the size of a golf ball or a fist, could sever the cable completely in a single, violent event. The consequences of such a rupture are almost too grim to fully contemplate. If the break occurs near the Earth's surface, the entire cable would unravel, whipping around the planet at hypersonic speeds, potentially causing devastation across entire continents. If the break happens higher up, perhaps near the geostationary orbit, the upper section would fly off into deep space, while the lower portion would fall back to Earth, burning up in the atmosphere and creating a rain of incandescent debris over a vast area. But the disaster wouldn't end there. The fragmentation of the cable itself would generate a massive new cloud of space debris, potentially triggering a cascading chain reaction known as the Kessler syndrome. This scenario involves one collision generating more fragments, which then cause further collisions, eventually rendering low Earth orbit and the crucial geostationary belt so cluttered with shrapnel that they become impassable and unusable for centuries. A space elevator catastrophe would be the ultimate trigger for this effectively locking humanity out of space and destroying countless satellites that modern life depends on for communication, weather forecasting, and navigation. To prevent this, a space elevator would require a defensive system of unprecedented scale and sophistication. First and foremost, we would need a global real-time monitoring network capable of tracking every piece of debris down to the size of a marble along the entire length of the cable. This would involve a constellation of ground-based radars, space-based telescopes, and sensors integrated into the cable itself, all feeding data into a central command that can predict collisions with high accuracy. But spotting the threat is only half the battle. We then need a way to avoid it. Actively moving the entire cable out of the path of incoming debris is an engineering nightmare. The cable has enormous mass and inertia. You cannot simply jerk it sideways. Any evasion maneuver would have to be slow, deliberate, and calculated to avoid inducing dangerous oscillations or waves that could travel along the cable and amplify stress. One proposed solution is to install small thrusters or electromagnetic actuators at regular intervals along the cable. These could provide tiny nudges to shift the cable's position slightly, but they would require their own power sources, fuel, and control systems, adding significant mass, complexity, and cost. Moreover, these systems would need to be incredibly reliable, as a failure could leave a section vulnerable. Another idea is to design the cable with a degree of flexibility or a segmented, redundant structure that can absorb impacts without breaking entirely. But this might compromise the very tensile strength we worked so hard to achieve. Alternatively, some have suggested protective measures like a sacrificial outer sheath that could be replaced periodically, or even deploying a diffuse barrier of gas or particles around the cable to disrupt smaller debris. But the practicality of maintaining such defences over 36,000 kilometres is dubious at best. Then there is the daunting challenge of repairs. Despite our best efforts, impacts will occur. So, we need a plan for fixing the cable when it gets damaged. Sending human repair crews is not feasible for most of the cable's length, especially in the harsh environment of space with its vacuum, extreme temperatures, and radiation. Instead, we would need an army of autonomous robotic climbers equipped with advanced inspection and repair capabilities. These robots would need to crawl along the cable, using sensors to find damage, and then perform complex tasks like welding, patching, or even splicing new sections of cable in place. The technology for such autonomous in-space repair does not exist today. Our current robotics are advanced for factory floors or even Mars rovers, but they are not designed for the precision required to handle a cable under tension in zero gravity while avoiding causing further damage. The robots would need to be capable of handling a variety of damage types, from micrometeoroid punctures to large gashes, and they would need to carry or have access to spare materials. The logistics of supplying these repair bots with power, parts, and instructions would be a monumental task. We might need orbiting depots stocked with cable segments and repair kits, or perhaps the robots could harvest material from the counterweight or other sources. The time factor is also critical. Damage must be detected and assessed quickly, and repairs must be completed before the damage propagates. This requires a robust and redundant communication system along the cable to relay data and commands without delay. Furthermore, the threat from debris is not static, it is accelerating. With the rapid deployment of mega constellations of satellites by various companies and countries, the number of objects in orbit is skyrocketing, increasing the probability of collisions and thus the generation of even more debris. Even with international guidelines for deorbiting old satellites, compliance is not universal, and the existing debris continues to pose a threat. Therefore, building a space elevator might force humanity to finally get serious about active debris removal on a global scale. Technologies for capturing and deorbiting debris, such as nets, harpoons, tethers, or lasers are in early development stages, but none are yet operational at the scale needed to clean up the orbital environment significantly. An international treaty and cooperation would be essential, as no single nation could manage this alone, and the space elevator would become a global infrastructure asset. The political and diplomatic hurdles are as immense as the technical ones. In essence, the problem of space debris transforms the space elevator from a purely engineering challenge into a complex socio-technological dilemma. It demands not only breakthroughs in materials and robotics, but also in global governance, space traffic management, and environmental stewardship of the orbital commons. Without a comprehensive solution that addresses both the prevention of collisions and the capability for rapid recovery, the space elevator remains a vulnerable giant, susceptible to destruction by a speck of paint travelling at hypersonic speeds. This underscores a profound irony. Our greatest bridge to the stars could be undone by the very litter we have already left behind. A stark reminder that our future in space depends on cleaning up our past messes and operating with far greater responsibility than we have thus far demonstrated. But surviving the external barrage of space junk is only part of the battle. The cable itself possesses a dangerous inner life, a constant, subtle motion that could tear it apart from within if left unchecked. This isn't a static, rigid pole sticking out into space. It's a dynamic, flexible structure, and it behaves more like a gigantic guitar string stretched between the earth and the heavens, susceptible to a complex symphony of forces that make it sway, vibrate, and oscillate in potentially catastrophic ways. The primary forces at play are the same ones that define its existence: Earth's gravity pulling down, and the centrifugal force from the planet's rotation pulling outward. But these are not steady, uniform pulls. The gravitational pull changes with altitude, creating a gradient, and the centrifugal force increases the further out you go. This alone sets up a fundamental tension that encourages movement. Now, add to this the gravitational influences of the Moon and the Sun. Just as their gravity causes ocean tides on Earth, they also exert tidal forces on the cable, constantly tugging and pulling it, causing it to lean and sway in a rhythmic, predictable, but powerful pattern. Then, there's the atmosphere itself. The lower portion of the cable, for the first 100 kilometers or so, is immersed in our planet's atmosphere. Here, it experiences atmospheric drag, winds, even subtle ones at high altitudes, push against the cable, and the simple fact that the cable is moving through the air as the Earth rotates creates a constant frictional force. All these forces combined, gravity, centrifugal, lunar and solar tides, and atmospheric drag, act on the cable simultaneously, making it oscillate in multiple directions and at multiple frequencies. It might swing back and forth like a pendulum, vibrate up and down like a plucked string, or develop complex, standing waves, where certain points along the cable have large amplitudes of movement, while other points, called nodes, appear still. These oscillations are not necessarily a problem at low levels. All structures have some natural vibration. The real danger emerges when a phenomenon called resonance occurs. Resonance is what happens when an external force applies periodic pushes at the exact natural frequency of the structure. Think of a child on a swing. A small push at just the right moment makes the swing go higher and higher. For the space elevator cable, DOT, if the rhythmic tug of the lunar tide, for example, matches one of the cable's many natural vibrational frequencies, the energy from that small tug can transfer efficiently into the cable's motion, causing the oscillations to amplify dramatically over time. The cable's immense length means it has not just one natural frequency, but a whole spectrum of them, from very slow, long wavelength sways to high frequency, short wavelength vibrations. This makes it vulnerable to resonance from a variety of sources. The consequences of unchecked resonance are dire. The oscillating cable would experience wildly fluctuating stress levels. At the peaks of the waves, the tension could spike far beyond the material's yield strength, causing it to stretch permanently or snap outright. Alternatively, the bending stresses from large amplitude sways could cause structural fatigue, leading to failure over time. The cable could literally whip itself to pieces. Furthermore, these oscillations would make the operation of the climbers, the vehicles going up and down, incredibly difficult. A climber trying to dock with or traverse a violently swaying cable would be a navigation nightmare, and the climber's own movement would add another source of excitation, potentially driving the cable into resonance itself. This climber-induced vibration is a serious concern. As a heavy climber ascends, it acts like a mass moving along a string, exciting different vibrational modes depending on its speed and position. Therefore, controlling these vibrations is not optional. It is absolutely critical for the survival of the entire system. But how do you control vibrations in a structure that is 36,000 kilometers long? You cannot simply build it stiff enough. The material must be flexible to some degree to handle the tension gradients, and making it overly rigid would add unacceptable mass. Instead, the solution must be active and dynamic. Engineers propose installing a system of active dampers and thrusters along the entire length of the cable. These would be small, distributed units that sense local vibrations and apply counterforces to cancel them out. It would be a massively distributed control system, a nervous system for the cable. Some dampers might work mechanically, like shock absorbers, dissipating vibrational energy as heat. Others might use electromagnetic forces or small, precisely timed rocket thrusters to give the cable a nudge in the opposite direction of its swing. This system would need to be incredibly sophisticated, with sensors continuously monitoring the cable's position, velocity, and acceleration, and processors running complex algorithms in real time to predict and counteract the motions. The scale of this endeavour is unprecedented. We are talking about thousands, perhaps millions, of these damping units installed along the cable, each requiring power, communication links, and immense reliability. Powering them is a challenge in itself. They could use solar power, but sections of the cable are in shadow for long periods. They might need to draw power through the cable itself, but that adds complexity and weight. The communication network to coordinate all these dampers would have to be flawless, with minimal latency, so that the countermeasures are applied in time to be effective. A delay of even a few seconds could allow a wave to build up to destructive levels. And all of this hardware, the dampers, thrusters, sensors, and wiring adds significant mass to the cable, which in turn increases the baseline tension and stress, creating a design trade-off where the solution to one problem exacerbates the fundamental challenge of material strength. Moreover, the system must be redundant. A failure of a few dampers in a critical section cannot be allowed to cause a cascade failure. There would need to be backup systems and the ability for neighbouring dampers to compensate. Maintenance of this active damping system introduces another layer of complexity, reminiscent of the repair challenges for micrometeoroid damage. Robotic climbers would likely be tasked with inspecting and servicing these dampers, but that means even more traffic on the cable, potentially exciting more vibrations. The control algorithms themselves are a frontier of engineering. They would have to model the cable's complex dynamics, which are influenced by so many variable forces, and adapt to changing conditions. It would be like trying to control the motion of a 100-kilometre long whip in real time while people are climbing along it and the wind is blowing. Testing such a system on Earth is impossible. We cannot build a full-scale model. We would have to rely on computer simulations and perhaps small-scale experiments in space. But the confidence in such a system would have to be extremely high before we entrust a multi-trillion-dollar structure to it. The problem of cable dynamics underscores that the space elevator is not a bridge you build and then forget. It is a living, breathing entity that requires constant, active management to keep it from destroying itself. It is a perpetual dance with physics, where a misstep in control could lead to a catastrophic finale. This challenge of oscillations and resonance is perhaps one of the most subtle yet insidious obstacles, because the forces are always present, always pushing and pulling, and the margin for error is vanishingly small. It demands a level of control system engineering that we have never attempted, for a structure of a scale we have never built, operating in an environment we are still learning to navigate. Without a robust and utterly reliable solution to this dynamic problem, the space elevator will remain a theoretical concept, forever vibrating itself to pieces in our imaginations before it can ever stand steady in reality. And while controlling those cosmic vibrations is a Herculean task, all that effort would be for nothing if the very foundation of the entire system, the Earth anchor, wasn't up to the challenge. This isn't just a big bolt in the ground. It's arguably the most complex and critical stationary facility ever conceived. A masterpiece of engineering that has to be as dynamic and responsive as the cable it holds. Think of it as the root system for a colossal tree whose branches reach into space. If the roots fail, the whole thing comes crashing down. The first and most non-negotiable requirement is location. The anchor must be situated on the equator. This is because the geostationary orbit, where the counterweight sits, is directly above the equator. Any deviation from this would mean the cable isn't vertical relative to the Earth's rotation, introducing immense lateral forces that would pull the entire structure down. But finding a spot on the equator isn't enough. It needs to be a place with exceptionally stable weather. Hurricanes, typhoons, and severe thunderstorms with their powerful winds and lightning are a constant threat. A direct lightning strike on the cable or the anchor station could fry its electronic systems in an instant, while hurricane-force winds could exert dangerous sideways loads on the cable, exacerbating those oscillations we just talked about. So, we're looking for a rare equatorial location with minimal severe weather activity, which significantly narrows down the options to places like a platform in the middle of the ocean or a specific, stable landmass. But even a stable location isn't a guarantee, which is why some designs propose a mobile anchor, perhaps a massive sea platform similar to a supersized oil rig that can actually move slowly to maneuver the cable out of the path of the worst storms. This adds an incredible layer of complexity, as now you have a floating city that must maintain its precise position while managing the trillion-dollar thread attached to it. Whether fixed or mobile, the anchor station's primary job is to handle the cable's tension. This isn't a static load, it's constantly changing. As the cable sways and vibrates, as climbers move up and down, adding and removing weight, and as temperature changes cause the cable to expand and contract, the tension at the anchor point fluctuates. The anchor must have an active tension management system, a set of giant winches or hydraulic dampers that continuously take in and let out a tiny bit of cable, compensating for these changes in real time. If it fails to do this, the cable could go slack, which might cause it to tangle, or the tension could spike beyond the material's limit and snap it. This active system would need to be incredibly robust and reliable, operating 24 hours a day, 7 days a week, for decades, with zero tolerance for catastrophic failure. Furthermore, the anchor is far more than just a clamp for the cable. It is the bustling spaceport where the entire operation begins and ends. It needs to house the infrastructure for launching and receiving the climbers. This includes massive loading and unloading bays for cargo, passenger terminals, fuel or energy storage facilities for the climbers, and immense repair hangars. The climbers themselves are complex vehicles, and they require regular maintenance and inspection. The anchor station would essentially be a combination of a seaport, an airport, and a rocket launch facility, all rolled into one. Then there's the power problem, the energy required to run the anchor station and to send power to the climbers, especially if using wireless energy transmission like lasers or microwaves, is staggering. We might be talking about building a dedicated power plant right next to the anchor, perhaps a nuclear reactor, to meet the continuous, massive demand. All of this hardware requires a state-of-the-art control center, the nerve center for the entire elevator. From here, engineers would monitor the cable's health along its entire length, track space debris, coordinate climber traffic, manage the active damping systems, and control the anchor's tension mechanisms. The data flow would be immense, requiring supercomputers and a global network of communication satellites. And with such a high-value asset, security is a paramount concern. The anchor station would be a target for terrorism or sabotage, so it would need to be a fortress with layered physical security, cyber defense systems, and possibly a small military presence. This brings us to the tangled web of geopolitics. The equatorial line passes through the territories of several nations and over international waters. Who gets to host this game-changing asset? If it's on land, it gives that country an enormous strategic and economic advantage, potentially leading to political tension or even conflict. If it's in international waters, who has jurisdiction? How are usage rights and tariffs regulated? The Outer Space Treaty of 1967 states that space is the province of all mankind, but a space elevator blurs the line between national airspace and outer space. It would likely require an unprecedented international consortium to build and manage it, a feat of diplomacy as challenging as the engineering. Getting multiple nations to agree on funding, ownership, operational control, and profit sharing would be a nightmare of negotiations. The host nation would have immense leverage, and other countries might be wary of becoming dependent on a single point of access to space controlled by a rival. This isn't just about building a structure, it's about navigating the complex and often contentious landscape of global politics. The anchor station also has to deal with more mundane but equally critical issues like logistics and supply chains. All the materials and personnel needed to operate the facility have to be transported to its often remote location, whether that's a tiny island nation or a platform in the middle of the ocean. This could involve building new ports, airports, and supporting infrastructure from scratch, all of which adds to the astronomical cost. The environmental impact of such a massive construction project and its ongoing operations would also need to be carefully assessed. The shadow of the cable alone could affect local weather patterns, and the constant comings and goings of support vessels and aircraft would disrupt local ecosystems. In every way, the Earth anchor is the linchpin. It's where the abstract dream of a space elevator meets the hard reality of dirt, steel, politics, and power grids. Its complexity is a microcosm of the entire project, containing within it all the challenges of engineering, logistics, energy, and human cooperation. Without a perfectly designed, built, and managed anchor, the magnificent cable reaching for the stars would be nothing more than the world's most expensive and dangerous loose thread. But securing the cable firmly to Earth is only half the equation. The other end, way out in space, demands something equally ingenious and massive, the counterweight. This isn't just a simple chunk of metal acting as a dead weight. It's a dynamically engineered component whose primary job is to use the Earth's rotation to its advantage, harnessing centrifugal force to pull the cable taut and keep the entire system stable. Think of it as the anchor in the sky, but one that's actively pulling outward, counteracting the relentless pull of gravity on the lower sections of the cable. Its location is absolutely critical, It must be positioned beyond geostationary orbit, typically around 36,000 kilometers up, where the centrifugal force due to Earth's spin becomes strong enough to balance the gravitational pull. If it were any closer, the cable would sag and collapse inward. If it were further, the tension might become unmanageable. So, what exactly could this counterweight be? One proposal is to build a massive space station, a hub of activity that also serves as the terminal for climbers arriving from Earth. This station would need to be colossal, weighing millions of tons, to provide enough outward pull. Another, even more ambitious idea is to capture a small asteroid and maneuver it into the correct position, effectively using a ready-made celestial object as the counterweight. This would avoid the need to launch all that mass from Earth, but it introduces its own mind-boggling challenges in asteroid capture, orbit adjustment, and securing the cable to it. A third option is to gradually assemble the counterweight by launching materials from Earth, perhaps discarded rocket stages or specially designed masses, and building it up over time. But this would require an immense number of launches and sophisticated in-space construction techniques. The design of this counterweight is not just about mass, it's about stability. Any shift in its position, any oscillation or drift, would translate directly into dangerous vibrations along the entire length of the cable. Imagine a tiny wobble in a weight at the end of a very long rope. That wobble can amplify into a massive wave. To prevent this, the counterweight must be designed with precise control systems, thrusters, gyroscopes, and dampers that can actively correct its position and orientation in real time, countering the subtle gravitational tugs from the moon, the sun, and even the uneven distribution of mass within the Earth itself. These perturbations are constant and would, if left unchecked, cause the counterweight to wander, inducing stresses that could fatigue and eventually rupture the cable. The placement of the counterweight isn't a one-time event. It's a continuous balancing act. Furthermore, the mass of the counterweight isn't arbitrary. It must be calculated precisely based on the mass and taper of the cable itself. If the counterweight is too light, it won't generate enough centrifugal force to keep the cable taut, leading to slackness that could cause the cable to buckle or tangle. If it's too heavy, it could overstress the cable, particularly at the geostationary point where tension is already at its maximum. This delicate balance means that the entire system, cable, dot, climbers, anchor, dot, and counterweight, must be designed as an integrated whole, with each component affecting the others. The logistics of getting the counterweight in place are a colossal undertaking in themselves. If we opt for the assembled mass approach, we're talking about thousands of rocket launches to transport the necessary materials. Even with reusable rockets, the cost, time, and environmental impact would be staggering. Each launch would have to deliver its payload to geostationary orbit or beyond, where robotic assemblers would then piece everything together in a complex orbital dance. If we choose the asteroid capture route, we first need to identify a suitable near-Earth asteroid of the right size and composition. Then, we'd need to develop technology to alter its trajectory gently, nudging it over months or years into the precise orbit required. This involves advanced propulsion systems, like ion thrusters or solar sails, and a deep understanding of orbital mechanics. Once the asteroid is in place, we'd have to attach the cable to it, which is no simple task on a rocky, irregular surface in microgravity. The counterweight also plays a role in the cable's deployment. One common deployment strategy involves launching the initial counterweight first, then spooling out the cable downward towards Earth while simultaneously extending a second cable upward as a balance. The counterweight's mass and stability are crucial during this delicate phase. Any instability could cause the cable to swing wildly or break. Moreover, the counterweight isn't just a passive mass, it's an active part of the elevator's operation. It could house power generation systems, like vast solar arrays, to beam energy down to climbers or to the anchor station. It could serve as a space dock, a manufacturing facility, or a habitat. This multifunctionality adds to its complexity but also to its value. However, integrating these functions without compromising the primary role of mass and stability is a significant engineering challenge. The systems inside the counterweight must be designed to minimize internal movement. For example, any rotating machinery or moving parts could induce tiny torques that affect the entire structure's balance. The safety implications of a counterweight failure are dire. If the counterweight were to detach or if its control systems failed, the cable would lose its tension, the upper portion would fly off into space, while the lower part would collapse toward Earth with catastrophic consequences. Therefore, the counterweight must have multiple redundant systems for position keeping and must be designed to withstand potential impacts from micrometeoroids or space debris, which are more prevalent in higher orbits. The long-term maintenance of the counterweight is another hurdle. Like the cable, it would require regular inspection and repair. Sending crews or robots to such a distant location is feasible but would be time-consuming and expensive. Any maintenance activity would need to be carefully planned to avoid disturbing the delicate balance of forces. The economic cost of creating the counterweight is a major barrier. Whether we build it or capture an asteroid, the investment required is in the hundreds of billions, if not trillions, of dollars. This necessitates international cooperation, raising all the same geopolitical issues as the anchor station. But now in the realm of space law and ownership, who controls the counterweight? How are resources allocated? The Outer Space Treaty provides some guidance, but the specifics would be a diplomatic minefield. In essence, the counterweight is far more than a simple weight. It is the keystone of the entire arch that is the space elevator. Its design requires a deep integration of orbital mechanics, materials science, control theory, and logistics. Without a perfectly designed and impeccably maintained counterweight, the elegant concept of a space elevator remains just that, a concept. It underscores that building a bridge to space isn't just about reaching up from Earth. It's also about having a firm, steady hand pulling from the heavens to make sure that bridge stays straight and true. This celestial anchor is as vital as the terrestrial one. And its challenges remind us that every part of this system is interconnected, each relying on the others to achieve the impossible dream of an elevator to the stars. The pursuit of this technology pushes the boundaries of what we can do in space, from massive construction to precise orbital control, and while the path is fraught with difficulty, the counterweight stands as a testament to human ingenuity in harnessing the fundamental forces of our universe to create something truly extraordinary. Now, with the anchor secured on Earth and the counterweight holding firm in space, we come to the heart of the entire operation, the climbers themselves, the vehicles that will actually travel up and down the cable, transforming this static structure into a dynamic transportation system. These aren't your ordinary elevators. They are sophisticated spacefaring vessels facing a journey that is unlike any other, a slow, arduous ascent fraught with unique challenges centered on propulsion, energy, and the sheer amount of time required. Imagine a train climbing a track that is 36,000 kilometers long, a track that is vibrating, swaying, and exposed to the vacuum of space and the remnants of Earth's atmosphere. The climber's primary mission is to transport cargo and potentially people from the ground to orbit. But its design is a puzzle of competing needs. It must be lightweight to avoid overloading the cable, yet robust enough to survive the journey. It must have a reliable propulsion system to climb, a sustainable power source to run that propulsion for days or even weeks. And it must navigate a path that is constantly in motion due to the cable's dynamics. Let's start with propulsion. How does a climber actually move? It doesn't use rockets in the traditional sense. Firing rockets against the cable would be inefficient and dangerous. Instead, most designs rely on motorized wheels or linear induction motors that grip the cable and crawl upwards, like a train on a vertical track or a robotic inchworm. This method provides a steady, controlled ascent, but it requires perfect traction and a mechanism that can handle the varying thickness and potential oscillations of the cable. The propulsion system must be incredibly reliable because a failure midway up the cable would be a disaster. A stranded climber would not only halt all traffic, but its dead weight would create a persistent stress point on the cable, potentially triggering dangerous resonances or even a local failure. Rescue would be nearly impossible. Sending another climber to retrieve it would be complex and risky. Therefore, the climbers would need multiple redundant drive systems, perhaps multiple sets of independent wheels or motors, so that if one fails, others can take over. This redundancy adds weight, which is a constant trade-off. Now, consider the energy required for this climb. This is arguably the climber's biggest challenge. The amount of energy needed to lift a mass against Earth's gravity all the way to geostationary orbit is enormous. For a climber carrying a significant payload, we are talking about energy equivalents that could power a small town for days. How do we get that energy to the climber? Running a physical power cable alongside the main cable is impractical. It would be far too heavy and would add immense stress to the structure. Batteries are also out of the question. The energy density of even the most advanced batteries is insufficient to power a weeks-long climb without making the climber impossibly massive. The most promising solutions involve beaming power to the climber from an external source. Two main technologies are proposed: laser beams and microwave power transmission. In both cases, a powerful ground-based or space-based transmitter would aim energy at a receiver on the climber, which would then convert it into electricity to run its motors. Laser beaming is attractive because lasers can be focused into a tight beam over long distances, but they are susceptible to atmospheric interference. Clouds, rain, and even turbulence can scatter or absorb the laser light, causing power drops at the worst possible moments. This would require the climber to have some onboard energy storage, like capacitors or batteries, to bridge short interruptions, again adding weight. Microwave power transmission is less affected by weather, but the beams are more diffuse, requiring very large transmitting and receiving antennas. A massive microwave transmitter on the ground, perhaps kilometers wide, would beam power to a large rectenna on the climber. However, the efficiency of this process over such distances is still a subject of research, and there are safety concerns about beaming such intense microwave energy through the atmosphere and airspace. Another idea is to have relay stations along the cable itself, perhaps powered by solar arrays, that can transfer power to the climber as it passes by. But this adds tremendous complexity to the cable's construction and maintenance. The power source for the transmitters is another issue. Beaming gigawatts of power continuously would require a dedicated power plant, likely nuclear or a vast array of solar panels built near the anchor station. The climber's journey time is a critical and often overlooked factor. This isn't a quick rocket ride. It's a slow, steady crawl. Why slow? Because going too fast would impose excessive dynamic loads on the cable. A climber moving at high speed is essentially a mass travelling along a string, and it can excite destructive vibrational modes, much like a bow moving across a violin string. Furthermore, the propulsion system might have practical speed limits based on its design. Therefore, ascent times are projected to be measured in days, perhaps even a week or more for a heavily laden climber. This long duration has several implications. First, it means the climber must be a self-contained life support system for any human passengers, with all the associated weight and complexity of air, water, food, and waste management for a prolonged period. For cargo, it means that anything time-sensitive might still be better suited for rocket launch. The slow speed also means that the climber will spend a long time in the Van Allen radiation belts, which are zones of intense radiation surrounding the Earth, without substantial shielding, which is heavy, electronic components could be damaged, and human passengers would receive a dangerous dose of radiation. This necessitates either developing lightweight radiation shielding or finding a way to traverse the belts more quickly, which circles back to the speed versus cable stress dilemma. The climbers also introduce a traffic management problem. Multiple climbers would be on the cable simultaneously to make the system economically viable. They would need to pass each other, which requires passing bays or sections of the cable with multiple tracks, coordinating their movements to avoid collisions, and to manage the complex interplay of their masses on the cable's oscillations would require a sophisticated, centralized air traffic control system in space. A climber descending presents its own set of challenges. It can't simply use regenerative braking the whole way, as the energy recovered would be difficult to store or dissipate. Some of the potential energy lost during descent could be converted to electricity and beamed back to the grid or used by other climbers. But this requires even more complex power management systems. The mechanical systems of the climber, especially the wheels or grips that contact the cable, would be subject to extreme wear and tear. They must operate reliably in a vacuum, withstand temperature extremes from the heat of the lower atmosphere to the cold of space, and possibly cope with atomic oxygen erosion at high altitudes. Maintenance would have to be performed at the anchor station and the counterweight station, requiring facilities that are essentially garages in space. The design of the climber is also affected by the changing gravitational environment. As it climbs, the effective gravity it experiences decreases, which might affect how its propulsion system grips the cable. Furthermore, the Coriolis effect, a result of the Earth's rotation, pushes the climber sideways as it ascends, which the climber must actively compensate for to avoid dragging the cable with it, adding another layer of control complexity. In essence, the climber is a marvel of systems engineering, integrating mechanics, power electronics, thermal control, and navigation into a package that must be both lightweight and supremely reliable. Its development is as formidable a challenge as building the cable itself, because without efficient, safe, and reliable climbers, the space elevator is just a very long and very expensive piece of string. They are the workhorses that must turn the theoretical promise of cheap access to space into a practical, daily reality. And every aspect of their design pushes the boundaries of our current technological capabilities, from beaming power across tens of thousands of kilometers to ensuring a motor doesn't fail a week into the climb. The journey of the climbers is a testament to the intricate and interconnected challenges of making the space elevator more than just a dream. It underscores that the system is a living, breathing entity where every component, from the massive counterweight to the smallest roller in a climber's drive mechanism, must work in perfect harmony for the entire audacious concept to succeed. Should the anchor station be moved to avoid a developing hurricane? Can the active damping systems be preemptively adjusted to counteract predicted jet stream-induced oscillations? This level of integration between weather prediction and structural control is unprecedented. The unpredictability of weather is the core of the problem. We can design for the average conditions, but it's the extreme outlier events, the once-in-a-century storm that arrives a year after the elevator is built, that pose the greatest risk. A failure to accurately predict a sudden, violent wind shear event or an upper atmospheric microburst could lead to a disaster. The atmosphere is the one environment we cannot control. We can only monitor and react. This makes the lower section of the space elevator the most vulnerable link in the chain, the part where the grand dream of space access meets the chaotic, messy, and powerful reality of Earth's climate. It's a reminder that before we can conquer space, we must first learn to coexist with and defend against the very environment that gave us life. An environment that does not care about our engineering marvels and will test them with every passing season. The solutions are not elegant. They are brute force applications of monitoring, redundancy, and robust design, adding yet more layers of complexity and cost to an already unimaginably complex project. Protecting the cable from the atmosphere isn't a side quest. It's a central, ongoing battle for survival, one that would demand constant vigilance and innovation for the entire operational life of the elevator. This atmospheric gauntlet, from the lightning-filled storms at the surface to the sand-blasting winds at the edge of space, represents a fundamental and inescapable challenge that grounds the space elevator concept firmly in the difficulties of our own planet, long before it can truly reach for the stars. But after navigating all those atmospheric dangers and engineering the perfect climber, we arrive at what might be the most mind-bending puzzle of the entire endeavour. How do you actually build the very first cable? This isn't like constructing a bridge or a skyscraper where you start from the ground and build upwards. This is a logistical paradox that turns conventional construction on its head. You cannot simply roll up a 36,000 kilometre long cable into a rocket and launch it from Earth all at once. The mass would be astronomical, and no rocket even on the drawing boards could carry such a payload. So, we are left with a seemingly backward approach. We have to start from space and build down towards Earth. The most widely accepted strategy involves beginning at the heart of the system, the geostationary orbit. Imagine first placing a massive counterweight, perhaps an captured asteroid or a pre-assembled station, precisely in geostationary orbit. This initial object serves as our anchor point in the sky. From this counterweight, we would begin a delicate and incredibly slow dual deployment process. One cable, often called the descent cable, is carefully spooled out downward towards the Earth's surface. Simultaneously, another cable is spooled outward, away from Earth, to act as the primary counterweight extension, ensuring the centre of mass remains correctly positioned at geostationary altitude. Think of it as lowering a thread from a floating balloon while also letting out another thread in the opposite direction to keep the balloon stable. This process is not fast. It would take months, maybe even years, as we painstakingly unspool the cable material, metre by metre, controlling the descent with exquisite precision. The machinery for this deployment would be a technological marvel in itself. It would need to operate autonomously in the vacuum of space, handling the cable with extreme care to avoid kinks, twists, or snags. Any sudden jerk or uneven spooling could send dangerous waves rippling along the nascent cable, potentially causing it to tangle or break. The tension must be managed perfectly throughout. Too little tension, and the descending cable could buckle or drift off course. Too much tension and it could snap. This requires a system of thrusters and sensors on the deployment platform constantly making tiny adjustments. As the descent cable gets longer and longer, it begins to enter the Earth's gravitational well more deeply, and the forces on it increase dramatically. The lower it gets, the more it is pulled by gravity, while the upper sections are still being pulled outward by centrifugal force. This creates a growing stress gradient that the deployment mechanism must account for in real time. Meanwhile, the cable is not descending into empty space. It is moving through the same hazardous environment we've already discussed, the zone of space debris and micrometeoroids. During this vulnerable deployment phase, the cable is a slow-moving, fragile target. A collision with even a tiny piece of debris, a paint chip or a metal fragment could sever the cable or create a critical weak point, since the cable is not yet fully tensioned and operational. Such a hit might cause the entire structure to whip around uncontrollably, rendering it useless. Therefore, Deployment would have to be coordinated with intense space debris, monitoring and avoidance maneuvers, adding another layer of complexity. The descent cable isn't just falling, it has to be guided. It must hit a very specific target. The anchor station on the Earth's equator. As the cable tip approaches the atmosphere, it enters another realm of danger. It must survive the heating and friction of re-entry, which is ironic for something coming down from space instead of going up. The cable material would need a protective sheath for this phase, or perhaps the tip could be equipped with a small heat shield. Then, it has to navigate the turbulent winds and weather systems we talked about before, all while being precisely steered towards its landing point. Capturing this cable tip and securing it to the anchor station is a feat of precision engineering. It might involve aircraft or drones snagging the cable mid-air, or a ship-based anchor station maneuvering to catch it. Once captured, the real work begins, anchoring it firmly and connecting it to the tension management systems. But the deployment isn't over yet. The outward cable is still being extended to build up the counterweight mass. This entire process is a balancing act of phenomenal proportions. A small error in the calculation of the counterweight's mass, a slight miscalibration in the deployment mechanism's speed, or a tiny drift in the orbital position of the deployment platform could compound over time, leading to a catastrophic misalignment. If the center of mass shifts even a little from the geostationary point, the entire cable will start to drift, pulling the anchor station off its foundation or putting unsustainable stresses on the cable. The deployment is also incredibly slow because of the energy involved. Unspooling the cable requires energy to overcome the gravitational pull and to manage the momentum. The systems involved can only operate so fast without risking instability. This slowness is a huge vulnerability. The longer the deployment takes, the more time there is for something to go wrong. A mechanical failure in the spooling mechanism stranded in geostationary orbit would be a disaster. There is no easy way to repair it. Sending a rescue mission would be complex and risky, and the partially deployed cable would be left to drift, potentially becoming a major hazard itself. The financial risk during this phase is immense. Billions of dollars would have been invested in developing the cable material, building the deployment platform, and launching the initial counterweight. A failure during deployment would mean losing it all, with nothing to show for the investment. This risk alone could deter investors and governments from funding the project. Furthermore, the deployment strategy assumes we have the capability to manufacture the cable material in space or spool it in a way that it can be deployed from a reel. We might need to have factories in orbit that can spin the cable continuously, which is another massive infrastructure project in itself. Alternatively, the cable could be manufactured in segments and connected in space, but that introduces thousands of potential failure points at the joints. Every connection would have to be as strong as the cable itself, which is a huge challenge for materials engineering. The psychological and operational pressure on the team managing this deployment would be unbearable. They would be guiding a single thread across 36,000 kilometers of hostile space, with every second carrying the potential for total failure. It is a task that requires not just advanced technology, but also immense patience and flawless execution. In many ways, this initial deployment is the ultimate test of the entire space elevator concept. It proves that building it isn't just about having a strong material. It's about orchestrating a cosmic-scale construction project with no margin for error. It is a delicate dance between gravity and momentum, a slow-motion ballet where a single misstep means the dancer falls, until we can demonstrate a reliable and safe method for deploying that first, fragile thread. The space elevator will remain a beautiful idea trapped in the realm of science fiction, a bridge we can imagine but cannot yet build. The challenge of the first thread is therefore the gatekeeper to the stars, and passing through that gate requires solving a paradox that defies how we build everything else. And after somehow solving the mind-bending puzzle of deploying that first fragile thread from space, we are immediately confronted with a chilling and entirely human problem, one that no amount of engineering genius can simply design away: the profound vulnerability of the entire system to deliberate attack. Imagine finally succeeding, after decades of work and trillions of dollars, in building this magnificent bridge to the stars, only to realize you have constructed the single most tempting target in human history. A space elevator would not just be a scientific marvel, it would be a strategic asset of epic proportions, and its very existence would make it a beacon for those who wish to cause maximum disruption, whether for political, ideological, or purely malicious reasons. Think about what it represents: a single point of failure for the entire global economy's access to space. Our modern world relies utterly on satellites for communication, navigation, weather, forecasting, financial transactions, and national security. If a significant portion of those satellites were launched and serviced by the elevator, then severing that one cable wouldn't just be an act of sabotage, it would be an act of economic and technological warfare, potentially plunging the world into chaos. The economic importance alone makes it a prize target. The entity controlling the elevator would wield immense power, collecting fees for every kilogram sent to orbit and potentially dictating terms of access. This concentration of power would inevitably create resentment and envy, fueling motives for attack from rival nations, terrorist organizations, or even non-state actors looking to make a statement. The cable itself, stretching across tens of thousands of kilometers, is physically impossible to protect in any conventional sense. You cannot post guards every meter along its length. You cannot build a fence around it. It passes through international airspace and then into the vacuum of space, through regions where no single nation has clear jurisdiction. This makes it uniquely vulnerable. A direct physical attack could take many forms. A terrorist group could use a hijacked aircraft or a drone to ram the cable at its lower levels. While the cable is designed to handle immense tension, a high-speed impact from a large object could create a critical weak point or even sever it completely. In a more sophisticated attack, a state actor could use an anti-satellite missile to target the cable at a higher altitude, creating a break that would be far more difficult to detect and repair immediately. The most insidious threat might come from asymmetric warfare, where a smaller, less powerful group uses unconventional means to attack a much larger foe. Imagine a scenario where a group attaches a small DOT, explosive device, to a climber during loading, set to detonate at a high altitude. Or they could use a swarm of small, difficult to detect drones to simultaneously attack multiple points on the lower cable. The methods are limited only by the imagination of those who wish to see it fail. Then there is the threat of sabotage from within. The construction and operation of the elevator would involve thousands of people from many nations, ensuring that every single engineer, technician, and security guard is completely loyal and beyond coercion is a logistical and psychological impossibility. A disgruntled employee or someone bribed by a rival could introduce a flaw in the software, a weakness in a material batch, or a physical tampering that leads to a catastrophic failure months or years later. This internal threat requires a level of personnel vetting and continuous monitoring that borders on dystopian. Because physical protection is so futile, security would have to rely almost entirely on a different kind of shield, a global network of intelligence, surveillance, and cyber defense. The anchor station would need to be a fortress with layers of physical security, air defense systems, and naval patrols to prevent any unauthorized approach, but that only protects the very bottom. For the rest of the cable, security would depend on a constant real-time surveillance system using every available asset, satellites with high-resolution cameras and radar to monitor the cable's entire length, ground-based sensors, and aerial drones. Any object approaching the cable would have to be identified and tracked instantly. This surveillance system would have to be so robust that it could distinguish between a piece of space debris and a deliberately launched projectile. And it would need the authority to take defensive action, which raises immense legal and ethical questions. The cybersecurity challenges are even more daunting. The elevator's operation would be managed by a complex network of computers controlling the climbers, the active damping systems, the power beaming, and the tension management. This network would be a prime target for hackers. A successful cyber attack could take over a climber and crash it into the cable, order the tensioning systems to release suddenly, or simply shut down the entire operation, causing economic havoc. Protecting this digital infrastructure from state-sponsored hackers and cyber terrorists would require defences far beyond what we have today, essentially creating a cyber fortress that is perpetually under siege. This leads to the geopolitical dilemma. The elevator's location on the equator means it will be in the territory of a specific nation or in international waters. If it is in a nation's territory, that country gains an enormous strategic advantage, which could destabilize global politics and lead to tension or even conflict. Other nations might view it as a threat and could be tempted to preemptively disable it in a crisis. If it is in international waters, who has the authority to protect it? An international consortium would likely be formed to manage it, but getting countries to agree on a shared security protocol is a diplomatic minefield. Would China, the United States, Russia, and the European Union all agree to jointly patrol and defend the cable? What happens if one member suspects another of harbouring attackers? The security of the elevator would require a level of international trust and cooperation that has rarely, if ever, been achieved in human history. It would necessitate new treaties and laws governing space assets and their protection. The mere possibility of an attack also introduces a permanent state of risk that would affect insurance costs, investment, and operational planning. The psychological impact of living under this constant threat would be significant for the people operating the system. Every minor alarm, every unexplained sense or reading would trigger a crisis response. The security apparatus needed would be vast, expensive, and intrusive, perhaps resembling a permanent global counter-terrorism operation focused on a single structure. Furthermore, the consequences of a successful attack are so catastrophic that they become a deterrent in themselves. The Day of Doom scenario we discussed earlier, where the cable wraps around the Earth, would cause destruction on a continental scale. This realization might deter some attackers, but for others, particularly extremist groups, that level of destruction might be the entire goal. This security threat is therefore not just another problem on a list, it is a fundamental, non-technical showstopper. It forces us to ask not just can we build it, but should we build it? And can we live with the consequences if it is attacked? Solving the material science and engineering is only half the battle. The other half is solving the much messier problem of human nature, politics, and global security, without a foolproof and likely globally enforced security framework. The space elevator remains a dream too dangerous to realise, a testament to the fact that our greatest technological achievements can be undone by our oldest and most persistent failings. The bridge to the stars must first be able to withstand the storms of our own world, and that may be the most difficult challenge of all. But even if we could somehow create an impregnable security shield around the entire structure, a new set of challenges emerges that are deeply rooted in the very environment the elevator must coexist with, forcing us to confront the unintended consequences of building something so monumental on our living planet. The environmental and aviation impacts of a space elevator are not secondary concerns. They are fundamental hurdles that could reshape regions of the Earth and redefine global transportation logistics. Let's start with the most immediate physical presence, the cable itself. This isn't an invisible force field, it's a solid object, and an incredibly long one, casting a continuous shadow as it stretches into the sky. While the cable would be relatively thin, its immense height means that as the sun moves across the sky, this shadow would sweep across the Earth's surface, creating a moving band of darkness. On a small scale, this might not seem like a big deal, but for the equatorial regions where the anchor would be located, this could have subtle but significant effects on local microclimates. The reduction in solar radiation, even for a brief period each day as the shadow passes, could influence local temperature, humidity, and wind patterns. It might affect plant life in the immediate vicinity, potentially altering small ecosystems that are finely tuned to consistent daily sunlight cycles. The cumulative effect over years is unknown, and studying this would require sophisticated climate modelling to predict any long-term changes to weather patterns in the anchor region. Then there is the issue of the anchor station itself. This would be a massive industrial complex, requiring immense amounts of energy, likely from a dedicated power plant. The construction and operation of this facility would have a local environmental footprint, including land use changes, potential water pollution if it's on the coast, and the generation of waste and emissions. If the power source is fossil fuels, that adds carbon emissions, though the hope would be for nuclear or large-scale solar to minimise this. But the environmental impact extends upwards. Into the atmosphere the cable passes through. The constant operation of climbers, launching and returning, introduces new elements into the upper atmosphere. During ascent, climbers could shed small particles or experience ablation on their surfaces, especially if they are moving through the atmosphere at high speeds, even if slowly. While each climber might release only a tiny amount of material, over years of continuous operation, this could lead to a gradual build-up of particulates in the stratosphere. Scientists are already concerned about the potential atmospheric effects of rocket launches and a space elevator, while potentially cleaner per kilogram of payload, would involve a much higher frequency of traffic. These particles could potentially affect atmospheric chemistry and even ozone depletion, requiring careful monitoring and mitigation. Furthermore, the risk of debris falling from the cable or from climbers is a real concern. During construction, and even during operation, there's a possibility of small components, tools, or pieces of the cable itself detaching and falling to Earth. While most would burn up in the atmosphere, larger pieces could survive re-entry, posing a risk to people and property on the ground. This necessitates a dedicated tracking and recovery system, and potentially no-fly and no-sail zones beneath the cable's path, which brings us to the single biggest logistical nightmare on Earth: aviation. The cable presents a physical obstruction of unprecedented scale to global air traffic. Commercial aviation routes crisscross the globe, including the equatorial regions. A permanent, immovable structure stretching from the ground to space would force a complete and radical redesign of the world's air traffic control system. Imagine a no-fly zone that isn't just a few miles wide around an airport, but a corridor that is effectively a wall reaching into the sky, stretching along the equator for the entire length that the cable's shadow and potential danger zone would dictate. This wouldn't be a simple adjustment. It would be a global aviation revolution. Every flight plan that currently crosses the equator would have to be rerouted to go around this exclusion zone. This would add significant distance to many long-haul flights, increasing flight times, fuel consumption, and carbon emissions. For example, flights from South America to Africa, or from Asia to South America, that currently take a Great Circle route over the ocean would now have to detour north or south, adding hundreds of kilometers to their journey. The economic ripple effects would be enormous. Airlines would face higher operating costs, which would likely be passed on to consumers in the form of higher ticket prices. Airports and air traffic control centres around the world would need to implement new procedures and update their software to manage this permanent rerouting. The complexity of coordinating this on a global scale is staggering, requiring unprecedented international cooperation through bodies like the International Civil Aviation Organization. The airspace around the anchor station itself would be the most restricted, akin to the airspace over a nuclear power plant, but on a much larger scale. This could disrupt local aviation, including medical evacuation flights, regional travel, and even military operations in the area. The anchor station would need its own air traffic control radar and systems to monitor and enforce this exclusion zone, and it would have to be defended against accidental or intentional incursions by aircraft. The presence of the cable also introduces a new hazard for high-altitude aviation and future hypersonic vehicles. While most commercial airliners fly below 10 kilometers, the cable exists far above that. However, the development of new aircraft that operate at higher altitudes could be hampered by this permanent structure. Moreover, the cable's oscillations, which we discussed earlier, mean that its precise position in the sky isn't entirely fixed. It sways. This adds another layer of uncertainty for any aviation activity that needs to happen even remotely near it. The environmental impact assessment for such a project would have to be global in scope and incredibly thorough. It would need to study not only the local effects at the anchor site, but also the atmospheric effects of increased particulates, the long-term climatic effects of the shadow, and the global impact of altered aviation routes on greenhouse gas emissions. This assessment would be a precondition for any serious attempt to build the elevator, and it would likely face intense scrutiny and opposition from environmental groups and governments concerned about these widespread effects. The project would have to demonstrate that its benefits outweigh these significant environmental and logistical costs. This is a classic example of a large-scale technological solution creating a cascade of second-order problems. The space elevator promises to reduce the environmental cost of reaching space by replacing polluting rocket fuels with electric climbers, but it does so at the expense of creating new environmental and logistical challenges on Earth. Balancing this equation is not just an engineering problem. It's a geopolitical and environmental one. It forces us to ask what kind of footprint we are willing to accept for the sake of space access. Does the benefit of cheap access to orbit justify the permanent alteration of equatorial regions and the global aviation map? There are no easy answers, and any proposal would need to include comprehensive plans for mitigating these impacts. Perhaps through technological innovations like cleaner climber designs, or by using the elevator to launch satellites that actively monitor and repair environmental damage. But the reality is that the space elevator is not a clean break from Earth. It is deeply entangled with it, and its construction would leave a permanent mark on our planet's environment and infrastructure, a reminder that our reach for the stars must always be grounded in a responsibility for the world we leave behind. The path to space, it turns out, is not just through the vacuum above, but through the complex, interconnected systems of our own biosphere and the intricate network of global human activity that we have built upon it. But beyond the environmental headaches and the aviation gridlock, we hit the mother of all practical roadblocks, the sheer, mind-boggling cost. We're not talking about a few billion here or there. We're talking about a financial black hole so deep it could swallow entire national economies without a trace. The initial capital investment required to build a space elevator is almost incomprehensible, with estimates ranging from hundreds of billions to several $1 trillion. To put that in perspective, the International Space Station, the most expensive single object ever built, cost around $150 billion over many years. A space elevator would make that look like a rounding error. This isn't just an expensive project. It's a financial endeavour on a scale humanity has never before attempted, dwarfing the Apollo program, the construction of entire national highway systems, and even the combined cost of all the world's largest infrastructure projects. And here's the brutal catch. This astronomical sum is just the entry fee, the money you have to spend up front on research, development, materials, construction, and deployment, with absolutely no guarantee of a return. The risk is colossal because it's all predicated on technologies that are, for the most part, still in their infancy. We are betting trillions of dollars on our ability to invent and mass produce a material that doesn't yet exist, to perfect construction techniques we've never tried, and to solve engineering problems that currently have no solution. No private company, no matter how wealthy, would shoulder that level of risk based on unproven science. Even the most ambitious tech billionaires would balk at the prospect of vaporizing their entire fortune on a single, high-risk project that could fail for 1,000 different reasons, from a material flaw to a space debris impact. Similarly, no single nation is likely to fund this alone. The political fallout from spending a significant portion of a country's GDP on a space elevator, while neglecting domestic issues like healthcare, education, and infrastructure, would be immense. It would be a political suicide mission for any government that tried it. Therefore, the only remotely plausible path forward is an unprecedented international consortium, a global partnership of nations and perhaps private corporations pooling their resources and sharing the risk. But this introduces a diplomatic and bureaucratic nightmare of epic proportions. Getting multiple countries to agree on anything is difficult. Getting them to agree on funding, design, location, ownership, and operational control of a space elevator is a Herculean task. The negotiations alone would take decades. Who gets the prime contracting jobs? Which countries' standards are used for safety and construction? How are the profits shared once? And if the elevator becomes operational, the potential for geopolitical friction is enormous. The host nation of the anchor station would hold a tremendous strategic advantage, potentially demanding a larger share of revenue or control, which other partners would resist. The legal framework for such a consortium doesn't exist and would have to be built from scratch, navigating a minefield of international space law, trade agreements, and national security concerns. Furthermore, the economic viability of the entire project hinges on a future that may not materialize. The elevator promises to reduce the cost of sending payloads to orbit from thousands of dollars per kilogram to perhaps just hundreds or even tens of dollars. This would undoubtedly unlock a new space economy, enabling large-scale space manufacturing, asteroid mining, and space-based solar power. But here's the problem. That robust space market doesn't exist yet. We are building a 100-lane highway to a destination that currently has only a few small villages. The demand needs to be created almost from scratch. The elevator's business case depends on a massive, sustained throughput of cargo to pay back the initial investment over many decades. If the demand isn't there, the elevator becomes a white elephant, a monument to ambition that bleeds money forever. This creates a chicken and egg dilemma. Investors won't fund the elevator until the space market is proven, but the space market can't truly explode until the cheap access of the elevator is available. While we struggle with these intractable problems, other technologies are already progressing and might render the elevator obsolete before it's even built. Reusable rockets, pioneered by companies like SpaceX, are already dramatically driving down launch costs. While they might not reach the theoretical lows of an elevator, they are a known, evolving technology that doesn't require a multi-trillion-dollar bet on unproven science. Other concepts, like launch loops or space planes, might also offer cheaper access without the immense fixed cost and single point of failure. The continuous development of these alternatives could ironically make the space elevator economically unviable. Why would anyone invest $1 trillion in a decades-long project when cheaper rocket launches are already a reality and improving every year? The financial calculations are also incredibly sensitive to the elevator's operational lifespan and maintenance costs. Even if built, the elevator would require constant, expensive upkeep. The cable would need continuous inspection and repair from micrometeoroid damage. The active damping systems would need power and maintenance. The climbers would need servicing, and the anchor station would have ongoing operational expenses. These recurring costs would eat into the revenue, extending the payback period even further. The interest on the initial debt alone would be staggering. Financing such a project would likely involve issuing bonds or taking loans with interest payments that could consume a large portion of the initial income for years. A minor technical problem that causes a shutdown for repairs could have catastrophic financial consequences, delaying revenue and increasing costs. Insurance would be another monumental expense, insuring a multi-trillion-dollar asset against failure from space debris, material fatigue, or even sabotage would require premiums that are themselves in the billions per year. The sheer scale of the investment also means that the opportunity cost is enormous. The trillions of dollars poured into the space elevator are trillions not spent on other pressing global issues, curing diseases, addressing climate change, alleviating poverty, or exploring the solar system with more conventional, lower-risk methods. Proponents argue that the long-term benefits would justify the cost, but convincing the world to make that sacrifice today for an uncertain payoff in 50 or 100 years is a nearly impossible sell. The economic feasibility of the space elevator is therefore not just a question of accounting, it's a question of vision, risk tolerance, and global cooperation on a level we have never seen. It demands a leap of faith that goes beyond engineering into the realms of finance, politics, and human psychology. Without a fundamental shift in how we fund and manage mega projects, and without the concurrent emergence of a booming space economy hungry for cheap transport, the space elevator will remain a dream confined to paper, a bridge to the stars whose first and most formidable anchor is buried deep in the hard reality of economics. The numbers simply don't add up yet, and until they do, this magnificent idea will be grounded not by gravity, but by the cold, hard calculus of dollars and cents. It's a stark reminder that our grandest visions are often limited not by what is physically possible, but by what is financially conceivable. And for now, the price tag for a space elevator is a number so large it exists more in the realm of imagination than in any spreadsheet or budget proposal. The path forward requires not only scientific breakthroughs but also a new economic paradigm, one where humanity collectively decides that the cost, as prohibitive as it seems, is a price worth paying for a permanent foothold in the cosmos. Until that day comes, the elevator remains the ultimate symbol of a future that is technologically within reach but financially out of grasp. Even if we could somehow magically solve the astronomical cost problem and assemble a global consortium willing to fund this trillion-dollar gamble, we would immediately be confronted by a silent, insidious, and relentless physical force that operates on a scale as vast as the elevator itself. The extreme and unceasing temperature fluctuations from the Earth's surface to the depths of space. This isn't a secondary engineering detail. It's a fundamental threat woven into the very environment the cable must endure. A problem of thermal dynamics that could slowly and methodically fatigue the structure to the point of catastrophic failure. Think about the journey the cable makes. It starts anchored at the equator, where surface temperatures can swing from the heat of a blistering day to the relative cool of a tropical night, a range of several tens of degrees Celsius. But that's just the beginning. As the cable stretches upward, it passes through the atmosphere, where temperatures can plummet to -50 or 60 degrees Celsius in the higher troposphere, then skyrocket to thousands of degrees in the thermosphere because of solar radiation, though with virtually no air to transfer that heat. The actual material temperature depends on its colour, texture, dot, and exposure. Finally, in the vacuum of space, the cable experiences the most extreme thermal environment possible, one side bathed in intense, unfiltered solar radiation, heating it to well over 100 degrees Celsius, while the shadowed side radiates heat into the void, cooling it to near absolute zero, minus 270 degrees Celsius or lower. This isn't a static condition. It's a constant, rhythmic dance of heating and cooling as the cable rotates with the Earth, moving in and out of sunlight every 90 minutes or so in lower orbits, and experiencing longer day-night cycles further out. This brutal thermal cycling means the cable material is continuously expanding and contracting. Every material has a property called the coefficient of thermal expansion, which dictates how much its length changes with temperature. For a cable 36,000 kilometers long, even a minuscule change per degree Celsius translates into hundreds of meters, or even kilometers, of total length variation over the entire structure. If the cable were rigidly fixed at both the anchor and the counterweight, this thermal movement would generate colossal forces. When a section heats up and tries to expand, it would be compressed, potentially causing it to buckle or warp. When it cools and contracts, it would be stretched even further, increasing the tension beyond the material's design limits and risking a snap. But the cable is already under immense and varying tension from gravity and centrifugal force, so thermal effects superimpose a new layer of complex dynamic stress. A localized hotspot could cause that section to expand slightly, reducing its tension and creating a slack point that might amplify oscillations or allow the cable to drift. A cold section contracting could increase local tension, creating a stress concentration that acts like a fault line in the structure. The most dangerous consequence of this endless thermal cycling is material fatigue. Fatigue is the progressive and localized structural damage that occurs when a material is subjected to cyclic loading. Even if the stress from each thermal cycle is far below the cable's ultimate tensile strength, the repeated application, day after day, year after year, can initiate microscopic cracks at points of imperfection or high stress. These cracks slowly grow with each temperature swing, gradually reducing the material's load-bearing capacity until it fails suddenly and without ample warning. For a space elevator designed to operate for decades, the number of thermal cycles is astronomical, numbering in the tens of thousands, making fatigue life a paramount concern. The material must not only be strong and light, but also possess exceptional fatigue resistance, a combination that is incredibly difficult to achieve. Furthermore, the thermal environment is not uniform along the cable's length. The lower section experiences atmospheric effects like wind chill and solar heating, while the upper sections deal solely with radiative heating and cooling. This creates longitudinal thermal gradients, where one part of the cable is expanding while another is contracting, inducing bending moments and shear stresses that the structure must withstand. There's also the issue of transverse gradients. The side of the cable facing the sun will be hot and expanded, while the shaded side is cold and contracted, potentially trying to bend the cable into a curve. This could lead to twisting or warping over time, complicating the path for climbers and adding unpredictable dynamic loads. To survive this thermal torture, the elevator's design must incorporate ways to accommodate these length changes without breaking or losing tension. One classical engineering solution is the use of expansion joints. These are specialized segments designed to flex and absorb thermal movement. On a space elevator, these joints would need to be distributed along the cable, allowing each section to expand and contract independently. However, Designing such a joint for a cable under millions of newtons of tension is a monumental challenge. The joint must be strong enough to handle the load, flexible enough to allow movement, and durable enough to withstand billions of cycles without wearing out. It would also be a point of vulnerability, potentially a weak link more susceptible to damage from space debris or material degradation. Another approach is to seek a material with a nearly zero coefficient of thermal expansion. Some advanced composites or ceramic materials can be engineered for minimal thermal expansion, but these often trade off other crucial properties like toughness, tensile strength, or ease of manufacture. For instance, materials like carbon-carbon composites or certain Invar alloys have low expansion, but they are either too heavy, not strong enough, or too brittle for the space elevator application. The dream material would need to combine the strength of carbon nanotubes with the thermal stability of a ceramic, a combination that currently exists only in theory. A more futuristic solution involves smart materials or active systems. Smart materials could change their shape or stiffness in response to temperature, actively compensating for expansion or contraction. For example, materials with embedded actuators or those utilizing phase changes could theoretically adjust their length to maintain a constant overall dimension. However, this technology is in its infancy, and introducing such complexity into a cable that must be incredibly reliable is a huge risk. Active thermal control is another possibility. This could involve circulating a coolant through hollow sections of the cable or using electrical heating elements to maintain a more uniform temperature. But the energy requirements for actively heating or cooling a structure of this scale would be prohibitive. Pumping coolant over tens of thousands of kilometers against gravity would require immense power, and the infrastructure needed, pumps, pipes, heat exchangers, would add enormous mass and complexity. Similarly, using electrical heating would demand a reliable power source and distribution system along the entire cable, which itself would be a massive engineering project. Even the cable's surface finish plays a critical role in thermal management. A highly reflective, mirror-like coating could minimize solar heating, while a black, radiative coating could enhance cooling on the shadowed side. But achieving and maintaining such a coating over the entire cable length, exposed to atomic oxygen erosion, ultraviolet radiation, and micrometeoroid impacts, is a daunting task. Any degradation of the coating would alter the thermal balance, leading to unexpected hotspots or cold spots and associated stresses. The thermal expansion problem also intimately interacts with other challenges we've discussed. For instance, the oscillations of the cable would be influenced by thermal stresses. A thermally induced length change could alter the cable's natural frequencies, potentially driving it into resonance with tidal forces or climber movements. The deployment of the cable would also be affected, since the material would expand and contract during construction. The initial tensioning and alignment would have to account for the expected thermal state in orbit. Moreover, the climbers themselves must be designed to handle the temperature variations they encounter during their multi-day journey. Their grip on the cable, their propulsion systems, and their internal electronics must all function reliably across a temperature range of hundreds of degrees. A climber that grips the cable too tightly on a cold, contracted section might slip on a hot, expanded one, or vice versa. The thermal design is therefore not just about the cable alone, but about the entire integrated system. In conclusion, while the search for a strong material often steals the spotlight, the challenge of thermal expansion and temperature fluctuations is a stealthy and equally formidable foe. It is a problem of persistence, of withstanding the slow, grinding wear of countless cycles that test the material's endurance to its very limits. Without a clever and robust solution to manage these thermal stresses, whether through passive design, active systems, or a revolutionary material, the space elevator could succumb not to a single dramatic event, but to the cumulative, invisible damage inflicted by the simple, unavoidable fact that things get bigger when hot and smaller when cold. This thermal gauntlet is yet another stark reminder that bridging the gap between Earth and space isn't just about reaching up. It's about surviving the profound physical realities of an environment that is utterly indifferent to our ambitions, where even the most subtle forces, when applied over such immense scales, can bring the grandest dreams crashing down. But just when you think you've accounted for every physical force trying to tear your space elevator apart, from the crushing weight of the cable itself to the relentless expansion and contraction from brutal temperature swings, another subtle yet powerful effect emerges from the very rotation of our planet, one that doesn't just stress the structure but actively tries to push it off course: the Coriolis effect. This isn't a force in the traditional sense like gravity or magnetism. It's what physicists call an apparent or fictitious force, a consequence of observing motion from within a rotating reference frame, like our spinning Earth. But for the climbers crawling up the space elevator cable, its effects are very real and incredibly disruptive, adding a whole new layer of navigational nightmare and structural concern to an already impossibly complex journey. To understand why this happens, imagine you're standing on a merry-go-round that's spinning clockwise. If you try to walk straight from the centre towards the edge, from your perspective on the merry-go-round, you won't walk in a straight line to the outside. You'll curve to your right. To someone standing on the ground watching, you're just moving in a straight line. But the merry-go-round is spinning under you. Now, scale that up to the size of the entire Earth. The planet is rotating from west to east, and the space elevator cable is fixed to it at the equator, extending up into geostationary orbit. A climber starting its ascent from the anchor station is already moving eastward at the same rotational speed as the Earth's surface, about 1,600 kilometers per hour, as the climber begins to move radially outward, away from the Earth's axis of rotation. It needs to conserve its angular momentum. Because it's moving to a point where the cable itself is moving faster eastward. Remember, points higher up on the cable are further from the Earth's centre and must move faster to complete one rotation per day. The climber, if left unchecked, would lag behind from the perspective of the cable, which is rotating with the Earth. This lag appears as a deflection. Specifically, the Coriolis effect pushes the climber in the direction of the Earth's rotation, which is eastward. So, as the climber ascends, it doesn't just go straight up. It experiences a constant force trying to push it to the east, making it drag the cable along with it. This causes the entire cable to bend backward, leaning to the west of its vertical position relative to the direction of rotation. This isn't a small, negligible lean over the immense height of the ascent. This deflection can be significant, adding a substantial lateral component to the cable's shape. This bending introduces several critical problems. First, it adds a new type of stress to the cable: lateral stress. The cable is meticulously designed to handle immense tensile forces being pulled apart, but now it's also being bent sideways. This bending moment creates compression on one side of the cable and tension on the other, which can lead to material fatigue and increase the risk of failure, especially at connection points or where the cable is already under maximum tension. The cable's natural oscillations, which we've discussed before, become even more complex when you add this Coriolis-induced curvature into the mix. The dynamic interactions between the swaying cable and the moving climber could amplify certain vibrational modes, making active damping systems work even harder. Second, and perhaps more immediately problematic, is the impact on the climber's navigation and control. The climber's guidance system cannot simply point straight up. It has to constantly compensate for this eastward push. If it didn't, the climber would exert a sideways force on the cable, exacerbating the bend and potentially causing it to rub against its own guidance rails or mechanisms, leading to wear and tear or even jamming. The climber must have a propulsion or steering system that actively counters the Coriolis force, effectively pushing it back towards the west to maintain its position relative to the cable's center line. This requires additional energy, which is a precious commodity on a journey that already demands immense power for the climb itself. The climber's power source, whether beamed via laser or microwave, must now supply extra energy for these corrective maneuvers, reducing the overall efficiency of the system and potentially limiting the payload capacity. The control algorithms for the climber become vastly more complicated. They must continuously calculate the required counterforce based on the climber's altitude, speed, and the local Coriolis parameter, which changes with latitude and altitude. Any delay or error in this calculation could cause the climber to oscillate from side to side, further exciting the cable's vibrations and creating a feedback loop of instability. This is not a one-time adjustment. It's a continuous process throughout the entire multi-day ascent. Furthermore, the Coriolis effect influences the cable's overall geometry and the placement of the counterweight. The constant eastward push on ascending climbers means the cable is perpetually under a slight torque, which must be balanced by the system. The counterweight's position might need to be adjusted to account for this persistent leaning, requiring its own station-keeping thrusters to fire more frequently, consuming fuel and adding to operational costs. The effect is also not symmetrical for ascending and descending climbers. A climber coming back down from space would experience the Coriolis effect in the opposite direction. It would be pushed westward. This means the guidance systems must be reversible and adaptable, capable of handling different force profiles depending on whether the climber is going up or down. This doubles the complexity of the control software and hardware. Traffic management on the cable becomes a nightmare when you consider the Coriolis effect. If multiple climbers are on the cable at once, each at different altitudes and moving in different directions, their combined Coriolis forces could interact in unpredictable ways, creating complex wave patterns along the cable that are difficult to model and control. Passing lanes or sections where climbers can overtake each other would need to be designed with these lateral forces in mind, ensuring that climbers don't collide or exert conflicting forces on the same section of cable. The structural design of the climber itself is affected. It can't be a simple, symmetrical box. It might need aerodynamic surfaces or thrusters positioned specifically for lateral control. These additions add weight, which again cuts into the payload capacity. The climber's grip on the cable must be secure enough to handle not just the vertical climb, but also the sideways pushes and pulls without slipping. The mechanical systems for gripping and moving must be robust to lateral forces, which could lead to increased maintenance and a higher risk of mechanical failure. From a psychological perspective, for any human passengers on board, this constant sideways force, even if compensated for, might be disorienting, while the climber's interior would be designed for comfort. The knowledge that you're being pushed sideways by an invisible force as you ascend to space could be unsettling, adding to the already significant challenges of human space travel. The Coriolis effect is a brilliant example of how a fundamental property of our planet, its rotation, creates a pervasive and inescapable challenge for a space elevator. It's not a problem you can solve with a stronger material or a thicker cable. It's a dynamic, continuous effect that must be actively managed every second of every climb. It demands sophisticated control systems, extra energy, and more complex mechanical designs, all of which drive up the cost, weight, and risk of the entire system. This effect underscores a critical point about the space elevator. It is not a static bridge, but a dynamic, living system that exists in a delicate balance with Earth's rotation. Ignoring the Coriolis effect would be like building a ship without a rudder, doomed to drift off course. Compensating for it requires a level of precision and active control that pushes the boundaries of our current engineering capabilities. It's another reminder that the path to the stars is littered with hidden obstacles, forces that are easy to overlook on a drawing board but become monumental in practice. The Coriolis effect might seem like a minor detail in the grand scheme of things, but for the space elevator, it's a persistent, nagging force that must be conquered metre by metre, all the way to geostationary orbit, making an already arduous journey even more treacherous and complex. In the end, overcoming it is not just about getting to space. It's about mastering the intricate dance of physics on a rotating world. A dance where every step must be perfectly calculated to avoid a catastrophic misstep. So, after grappling with the constant push and pull of the Coriolis effect and all the other dynamic forces trying to destabilize the elevator, we arrive at a simple, stark reality. Building this thing is only the beginning. Keeping it operational for decades is a never-ending battle against decay, damage, and the relentless harshness of the space environment. A battle fought across 36,000 kilometers of the most inaccessible real estate imaginable. Maintenance and repair for a structure of this scale isn't just a routine chore. It's a continuous, Herculean effort that would define its entire operational life, requiring technologies and logistics we can barely conceive of today. Imagine the sheer length involved. We are talking about a cable long enough to wrap around most of the Earth's equator, a single structure exposed to every conceivable hazard from the humid, stormy atmosphere to the airless, radiation-blasted void of space. You cannot just wait for something to break. You have to constantly be looking for the tiny cracks, the subtle wear, the microscopic damage that could, if left unchecked, grow into a catastrophic failure. This demands an perpetual inspection regime. Fleets of specialized robotic inspectors would need to crawl, slide, or float along the entire length of the cable, day and night, year after year. These wouldn't be simple machines. They would be sophisticated mobile laboratories equipped with suites of sensors, high-resolution cameras, LiDAR, ultrasonic probes, and X-ray scanners to peer deep into the cable's structure, searching for the telltale signs of fatigue, impact damage from micrometeoroids, or corrosion from atomic oxygen. They would be the first line of defense, the ever-vigilant sentinels on a thread stretching into the cosmos. But spotting a problem is the easy part. Fixing it is where the true challenge begins. The environment for these repairs is unforgiving. For most of the cable's length, repairs would have to be conducted in the hard vacuum of space, with its extreme temperature swings and intense radiation. In the lower sections, within the atmosphere, repairs would face high winds, lightning risks, and severe weather. Sending human repair crews is utterly impractical for the vast majority of the cable. The time, cost, and life support requirements for a spacewalk over 30,000 kilometers high are prohibitive, not to mention the sheer danger involved. Therefore, the entire repair system would have to be almost entirely robotic and autonomous. We are talking about armies of repair bots, deployed from the anchor station or from orbiting depots, capable of navigating to a precise coordinate on the cable and performing complex surgical procedures on it. Imagine a robot that has to locate a hairline crack caused by a tiny piece of space debris. It would need to clean the area, perhaps using a small grinder or a laser to remove damaged material, then apply a patch or inject a healing resin, and finally, cure it in place, all while maintaining a secure grip on a cable that might be vibrating slightly, and while operating in zero gravity with no human guidance. The level of autonomy required is far beyond anything we have today. Our current robotics are amazing for controlled environments like factories or even for rovers on Mars, but they operate with significant human oversight and with time delays that are acceptable for planetary exploration. For a space elevator, the repair robots would need to make split-second decisions based on complex sensor data. A communication delay of even a few seconds from a ground controller could be the difference between a successful patch and a botched job that makes the damage worse. These robots would need artificial intelligence capable of assessing damage, selecting the right repair protocol from a library of options, and executing it with the precision of a master craftsman, all on their own. The logistics of supporting this perpetual repair operation are a nightmare in themselves. Where do you store all these robots and their spare parts? You would need maintenance depots strategically located along the cable, perhaps at the anchor station, at geostationary orbit, and at the counterweight. These depots would themselves be small space stations, requiring their own power, life support for any occasional human technicians, and resupply from Earth. The cost of launching all the necessary materials, new cable segments, raw materials for patches, propellant for the robots, and replacement parts would be a continuous, massive drain on the elevator's economics. It would be like supporting a dozen international space stations, but strung out along a single line. The repair robots would also need a way to move along the cable. They might use their own grit-based propulsion, similar to the climbers, or they could be launched from stations and use tethers to rendezvous with specific points. Either way, their movement must be carefully coordinated with the climber traffic control system to avoid collisions. A single repair mission could require shutting down a section of the cable for hours or days, halting all climber traffic and costing millions in lost revenue. This makes scheduling and efficiency absolutely critical. Furthermore, the types of damage are diverse and unpredictable. A micrometeoroid impact might create a clean, small hole, while a larger piece of debris could cause a ragged tear. Solar radiation could embrittle the cable's outer coating over time. Thermal cycling could cause fatigue cracks at stress points. The repair systems would have to be versatile enough to handle all these scenarios. Some repairs might be temporary, just a patch to hold until a more permanent solution can be implemented, which might involve splicing in a new section of cable, splicing two ends of a super strong cable under tension in zero gravity is a task that sounds like science fiction. It would require incredibly precise alignment and a connection method that preserves 100% of the cable's strength. The financial cost of this endless maintenance is staggering. The initial investment in the repair robots, the depots, and the spare parts inventory would be in the billions, and the ongoing operational costs would be a permanent fixture on the balance sheet. Insurance companies would demand proof of a robust maintenance program before offering any coverage, and the premiums would be astronomical. The human factor is also immense. While robots would do the physical work, a small army of engineers, technicians, and controllers on the ground would be needed to monitor the system, analyze inspection data, plan repair missions, and manage the logistics. The control center would be a hive of activity 24/7, with screens showing the real-time health of every meter of the cable. The psychological pressure on the team would be enormous. A missed alert or a misdiagnosed problem could lead to the loss of the entire structure. In essence, the space elevator would never be finished. It would be a living, breathing entity in a constant state of healing itself. Its operation would be a testament not just to our ability to construct wonders, but to our ability to sustain them against all odds. This perpetual struggle against entropy underscores a profound truth about ambitious engineering. The true cost of a mega project isn't just in its construction, but in its care and feeding over a lifetime. Without a revolutionary advance in autonomous robotics and a logistical framework that can support a continuous globe-spanning repair operation, the space elevator would be doomed to a short, spectacular life. The maintenance challenge is therefore the final, quiet guardian at the gate, a reminder that our grandest structures are only as strong as our commitment to keeping them standing, day after day, year after year, in the face of a universe that is constantly trying to tear them down. It is a battle of attrition fought with robots and sensors, a war against wear and tear that would be waged silently in the void, determining whether the bridge to the stars remains open or becomes just another piece of cosmic debris. The answer will determine whether the elevator is remembered as a bridge to a new future or merely the largest contributor to a celestial junkyard. And now we must confront the most sobering and terrifying aspect of the entire space elevator concept. The one scenario that transcends engineering failure and enters the realm of existential threat: the catastrophic collapse. This isn't just about a broken machine. It's about an event of biblical proportions, a doomsday scenario that would dwarf any natural disaster in recorded history, and whose mere possibility is a powerful argument against ever building such a structure. The failure of a space elevator would not be a local incident. It would be a global cataclysm, and understanding its mechanics is a crucial, if horrifying, part of the feasibility study. The specific nature of the disaster depends entirely on where the cable fails. Let's consider the two most likely and most devastating breakpoints. First, imagine a rupture occurring very close to the anchor station on Earth. This could be caused by a terrorist attack, a massive structural flaw, or a collision with a large aircraft. The instant the cable parts near the bottom, the balance of forces that held the entire system taut is obliterated. The counterweight at the top, no longer held down by the weight of the cable beneath it, is now subject only to the centrifugal force of Earth's rotation. This force immediately flings the counterweight, along with the entire 36,000 kilometre length of cable still attached to it, out into space on a new, untethered trajectory. But the story doesn't end there. As the cable is flung away, it is still wrapped around the Earth. Think of it as a gigantic, ultra-taut string that has been cut at one end. The released tension would send a wave of energy racing along the cable's length. The entire structure would begin to unravel from the planet, whipping laterally at hypersonic speeds. It would wrap itself around the Earth's equator multiple times, like a string winding around a ball. The kinetic energy involved is almost beyond comprehension. The cable, weighing millions of tons, moving at orbital velocities, would act as a planetary-scale lash. It would scour everything in its path clean. Cities, mountains, forests. Nothing would withstand the impact. The cable would slice through the atmosphere, creating deafening sonic booms and igniting the air from friction, effectively creating a continuous incandescent band of fire around the planet's midsection. The destruction would be absolute along a swath thousands of kilometers wide, effectively sterilizing the equatorial region and causing a mass extinction event. The secondary effects would be just as catastrophic. The immense energy transfer into the atmosphere would trigger unprecedented global storms and climate disruption. The dust and debris thrown up would block out the sun, potentially initiating a volcanic winter-like scenario that could last for years, collapsing agriculture and ecosystems worldwide. Now, let's examine the second nightmare scenario, a break high up near the counterweight. This could happen from a major space debris impact or a critical failure of the counterweight itself. In this case, the dynamics are different, but the outcome is equally dire. The section of cable above the break, including the counterweight, would fly off into solar orbit, lost forever. However, the much larger section of cable below the break, tens of thousands of kilometers of it, is now no longer held up by the centrifugal force from the counterweight. It is subject only to gravity. This colossal length of cable would then fall, but it wouldn't fall straight down. Because it was moving at orbital speeds, its fall would be a gradual, decaying orbit around the Earth. Different segments of the cable would re-enter the atmosphere at different times and places, creating a continuous global rain of incandescent debris over the course of several days. Imagine thousands of meteor showers happening simultaneously all across the planet. Each piece of cable, heated to thousands of degrees upon re-entry, would streak across the sky like a lightning bolt, impacting the ground with tremendous force. While the larger sections might break up, the potential for chunks of this super strong material to survive and strike populated areas is high, causing widespread fires and destruction. The entire planet would become a target in a random unpredictable bombardment. The economic and human cost of either scenario is immeasurable. It would not just set back space exploration, it would set back human civilization for centuries. The global transportation and communication networks that rely on satellites would be obliterated, either by the direct physical impact of the cable or by the resulting debris field in orbit from the disintegration of the counterweight station and any climbers on the cable at the time of failure. The psychological impact on humanity would be profound. The very symbol of our technological ascent would have become the instrument of our devastation. This doomsday potential fundamentally changes the risk calculus of the space elevator. It is no longer just a high-risk engineering project. It is a planetary-scale threat. This necessitates a field of study dedicated solely to risk analysis and mitigation for such a collapse. Engineers would need to model every possible failure mode with supercomputers, trying to predict the chaotic dynamics of a breaking cable thousands of kilometers long. They would need to design elaborate and utterly reliable failure containment systems. Perhaps one idea is to segment the cable with explosive charges designed to sever it into smaller, less destructive pieces in the event of a catastrophic failure, though the logic of using explosives on a structure you're trying to protect is fraught with its own perils. Maybe the system would require multiple, redundant cables so that if one fails, the others can hold the load, but this multiplies the cost and complexity. The political and insurance implications are mind-boggling. What nation would agree to host the anchor station, knowing it paints a target on their entire continent? How could any insurance company possibly underwrite a structure whose failure could cause trillions of dollars in damage and billions of casualties? The liability would be infinite. The very existence of the elevator would create a permanent sword of Damocles threat hanging over all of humanity. This risk is perhaps the most potent weapon in the arsenal of those who oppose the space elevator. It forces a philosophical question. Do we have the right to build something whose failure could end our civilization, even if the probability of that failure is deemed astronomically low? History is littered with engineering projects declared unsinkable or fail-proof. The sheer scale and novelty of the space elevator mean that unforeseen failure modes are a virtual certainty. The collapse scenario is therefore not just a technical problem to be solved, it is a moral and existential boundary. It reminds us that our reach must be tempered by wisdom, and that our grandest ambitions must be weighed against their potential for ultimate ruin. Before the first gram of cable material is ever produced, we must have an answer to the question of what happens when it all comes crashing down. Without a credible fail-safe plan to manage a total collapse, a plan that can guarantee with near absolute certainty that the debris will fall harmlessly into the ocean or burn up completely, the space elevator will remain, and perhaps should remain, a dream deferred. The path to the stars cannot be paved with the potential for terrestrial oblivion. This ultimate challenge is a humbling reminder that for all our ingenuity, we are still custodians of a fragile world, and some bridges, once built, cannot be uncrossed. But even if we could somehow engineer a fail-safe system to prevent a catastrophic collapse and manage the monumental technical hurdles, we would then plunge headfirst into a tangled web of legal and geopolitical challenges that are every bit as complex and daunting as the physics and engineering. The space elevator doesn't exist in a legal vacuum. It would stretch from the sovereign territory of a nation through international airspace and into the realm of outer space, creating a jurisdictional labyrinth that current international law is completely unprepared to handle. The first and most immediate question is, who owns it? If the anchor station is located within a specific country's territory, that nation would naturally claim jurisdiction over the entire structure, arguing that it is an extension of its territory into space. This is a legal theory known as the flag principle, similar to how a ship on the high seas is under the jurisdiction of its flag state. However, other nations would vehemently oppose this, arguing that the portion of the cable beyond the Kármán line, the unofficial boundary of space, falls under the Outer Space Treaty of 1967, which declares that space is the province of all mankind and not subject to national appropriation. So, we have an immediate conflict. Is the space elevator a sovereign territory or an international space asset? This isn't just an academic debate. It has profound implications. The host nation could unilaterally set toll rates, control access, and even deny passage to certain countries, effectively holding the world's space economy hostage. This would be an unacceptable concentration of power for most of the international community. To avoid this, the elevator would likely need to be governed by an international consortium similar to the International Space Station, but on a much larger and more complex scale. Creating such a consortium would be a diplomatic minefield. Negotiating the founding treaty would take years, if not decades. How would voting rights be allocated? Based on financial contribution, technological contribution, population? The potential for deadlock is enormous. Then there's the question of liability. The Outer Space Treaty holds states liable for damage caused by their space objects. If a piece of the elevator breaks off and damages another satellite or causes harm on Earth, who is liable? The host nation? The entire consortium? The private company that built the climber that caused the fault? The legal framework for apportioning blame and financial responsibility would need to be crystal clear, or no insurance company would ever underwrite any activity related to the elevator. The elevator also blurs the line between airspace and outer space. National airspace is sovereign, but there is no internationally agreed upon boundary where airspace ends and outer space begins. The elevator, a physical structure, would pass through this ambiguous zone, creating continuous legal friction. Would overflight rights be required for the portion of the cable in a nation's airspace? How high up does a country's airspace extend? These are unresolved questions that the elevator would force to the forefront. Every time a climber ascended, it would theoretically be passing through the airspace of multiple nations, requiring permissions and clearances that would grind operations to a halt if not managed by a seamless international agreement. The choice of the anchor station location itself is a geopolitical nightmare. The elevator must be on the equator. This limits options to a handful of countries and open ocean. Building it in a country like Ecuador, Indonesia, TTIC, or Kenya gives that nation immense leverage. It could demand exorbitant fees, renegotiate terms, or even nationalize the asset in a future political shift. Building it in international waters seems more neutral, but it introduces other problems. It would require a massive sea platform, which would then exist in a legal grey zone. While the UN Convention on the Law of the Sea governs economic zones in the high seas, its application to a permanent space launch facility is untested. Furthermore, a sea-based anchor would be more vulnerable to piracy, terrorism, or blockade by a hostile naval power. The security of the elevator would require a permanent international naval presence. Another layer of complex coordination and potential conflict. The operational regulations would also be a source of contention. How are safety standards set and enforced? Which countries' environmental regulations apply to the construction and operation of the anchor station? How are disputes between consortium members resolved? Is there an international court with binding authority? The elevator would necessitate the creation of a whole new body of international space law, a process that is historically slow and fraught with competing national interests. The potential for weaponization is another serious concern. While the Outer Space Treaty prohibits placing weapons of mass destruction in orbit, it doesn't ban all military use. A nation controlling the elevator could argue for the right to patrol and protect it with military forces. Others would view this as the militarization of space. The elevator could be seen as a strategic asset to be defended or a threat to be neutralized in times of international tension, making it a flashpoint for conflict. Even without malicious intent, the elevator creates a single point of failure for the global space infrastructure, a terrifying prospect for national security planners worldwide. The economic regulations are equally complex. How are tariffs set? Is access granted on a first-come, first-served basis, or are there quotas? What happens if a climber from one country collides with a climber from another? The need for a universal air traffic control system for space, centered on the elevator, is absolute, but achieving it requires surrendering a degree of national control that many countries may be unwilling to give. In essence, the space elevator is not just a technical project, it is a test of global governance. It demands a level of international trust, cooperation, and legal integration that humanity has never before achieved. It requires us to move beyond 19th century concepts of absolute sovereignty and into a new era of shared responsibility for a shared asset. The legal and geopolitical challenges are therefore perhaps the most intractable of all. We can perhaps imagine inventing a new material, but can we imagine inventing a new form of politics? The success of the space elevator hinges on our ability to overcome our deepest instincts for competition and control and to build a legal framework that is as strong, flexible, and resilient as the cable itself. Without this, the bridge to the stars will be broken long before the first climber ever leaves the ground, not by a failure of engineering, but by a failure of diplomacy. This grandest of human endeavours holds up a mirror to our political divisions, showing that the final frontier is not just space, but our own ability to cooperate on a planetary scale. So, after navigating that gauntlet of legal and geopolitical nightmares, we arrive at a final, fundamental question that puts the entire space elevator concept into perspective. Is this colossal, risk-laden structure even the right path forward? Or are we trying to solve a problem that other, more nimble technologies are already beginning to crack? The space elevator has captivated our imaginations for decades as the ultimate symbol of cheap and easy access to space. But while we've been wrestling with its seemingly insurmountable physics and political problems, the world of rocketry has been quietly undergoing a revolution that might make the elevator obsolete before we even lay its first foundation. The promise of the space elevator was always its potential to slash the cost of reaching orbit from thousands of dollars per kilogram to just hundreds or even tens. But we have to ask if that goal is still best served by a single fragile, trillion-dollar mega project. The most compelling argument against the elevator comes from the rapid and dramatic progress in reusable rocket technology. Companies like SpaceX have demonstrated that landing and reflying rocket boosters is not just science fiction. It's a working, profit-driving business model. The Falcon 9 and the Falcon Heavy have already drastically reduced launch costs, and the fully reusable Starship system promises to push those costs down even further. This isn't a theoretical future, it's happening right now. These rockets are not perfect. They still involve controlled explosions and carry their own fuel, but they are evolving rapidly, becoming more reliable and efficient with each iteration. The key advantage they hold over the space elevator is their inherent flexibility. A rocket can launch from multiple locations, reach various orbits, and be deployed for missions beyond Earth, like to the Moon or Mars. A space elevator, by contrast, is fixed to one spot on the equator and is primarily useful for reaching geostationary orbit. If your destination is a polar orbit or a lunar transfer trajectory, the elevator offers little benefit, and you might still need a rocket anyway. The development cycle for rockets is also far quicker. We can test, fail, iterate, and improve new rocket designs in a matter of years, whereas the space elevator would require a decades-long, all-or-nothing commitment before we even knew if it worked. This iterative approach to rocketry allows for continuous innovation and risk management, something the elevator's monolithic design cannot accommodate. Beyond reusable rockets, other alternative concepts are vying for attention, each with their own potential to provide cheap access to space without the elevator's baggage. One promising area is beam-powered launch systems. The idea here is to leave the heavy power source on the ground and use either powerful lasers or microwaves to beam energy to a vehicle as it ascends. This vehicle, often called a light craft, could be much lighter since it wouldn't need to carry all its own fuel. It would have a heat exchanger on its underside that the beamed energy would superheat, creating thrust as the air expands and blasts outwards. For the initial atmospheric portion of the flight, this could be incredibly efficient. While this technology is still in early experimental stages, it avoids the need for a physical tether stretching into space, sidestepping the entire nightmare of material strength, space debris, and cable dynamics. The infrastructure would be complex, requiring massive power plants and precise aiming systems, but it would be confined to a ground-based facility, making it easier to secure and maintain than a 36,000-kilometre cable. Another fascinating alternative is the concept of a space fountain. This is a truly mind-bending structure that uses a stream of magnetically levitated pellets shot upward through a tube to support a stationary platform high above the Earth. The pellets are deflected at the top and sent back down, transferring their momentum to keep the platform aloft. It's like building a tower without needing compressive strength, but it requires a constant input of energy to keep the pellet stream moving. While theoretically possible, it introduces its own set of immense engineering challenges, such as managing the incredible speeds of the pellets and ensuring perfect magnetic control. However, it highlights that human ingenuity is exploring multiple pathways to space, not just the elevator or rockets. Perhaps the most logically compelling argument for abandoning the Earth-based space elevator is to consider building it elsewhere. The concept makes far more sense on worlds with lower gravity and no atmosphere, like the Moon or Mars. The tension in the cable is directly related to the gravitational pull and the rotational speed of the body. The Moon's gravity is only 1/6 of Earth's, and its required orbital velocity is much slower. This means the material strength needed for a lunar space elevator is within reach of existing technology. We could build one today with materials like Kevlar or Xylon. A lunar elevator would not reach all the way to the Moon's surface, but would connect a point in low lunar orbit to the surface, drastically reducing the fuel needed to land and take off from the Moon. This could be the key to establishing a sustainable lunar economy, mining water ice from the poles and shipping it to a depot in orbit for refueling missions to Mars and beyond. Similarly, a Mars elevator would be far more feasible than an Earth one, given its lower gravity. By proving the technology on these smaller bodies first, we could gain the operational experience and confidence needed to even contemplate an Earth version, all while reaping immediate economic benefits. Then there are more radical ideas like the launch loop or orbital rings, which involve constructing hypersonic magnetic railways or rings around the Earth to accelerate payloads to orbital velocity. These concepts are even more speculative than the space elevator, but demonstrate that the design space for space access is vast and largely unexplored. The continuous development of these alternatives creates a moving target for the space elevator. Every year that rockets get cheaper and more reliable, the economic case for the elevator weakens. The elevator's business model relies on a future with massive demand for space launch capacity. But if rockets can satisfy that demand at a competitive price with greater flexibility and lower upfront risk, then investors and governments will have little incentive to fund the elevator's development. The resources required for the elevator, the trillions of dollars, the decades of international cooperation, the scientific manpower, could be invested into improving these alternative technologies instead, potentially yielding faster and more certain returns. This leads to a profound irony: the very pursuit of the space elevator, by driving research in advanced materials and construction techniques, might indirectly contribute to the technologies that ultimately replace it. The knowledge gained from studying carbon nanotubes for the elevator could benefit other industries, and the lessons in large-scale space construction could be applied to building orbital habitats or solar power satellites, accessed by the very rockets the elevator was meant to supersede. In the end, the space elevator stands as a beautiful, elegant, and inspiring concept, a testament to human ambition. But it also serves as a cautionary tale about technological overreach. It challenges us to think critically about the best way to achieve our goals, not just the most dramatic. The future of space access is likely to be messy, diverse, and incremental, built on a foundation of reusable rockets, supplemented by beam-powered systems for specific roles, and eventually expanded by lunar and Martian elevators that open up the solar system. The Earth-based space elevator may forever remain a brilliant idea whose time never came, not because it was impossible, but because something better came along. Our journey to the stars will probably not be on a slow elevator climb, but on a series of ever-improving rockets, each one carrying us a little further, a little cheaper, and a little faster, proving that sometimes the best path to the future isn't a single, monumental leap, but a continuous, relentless climb.